The story begins far outside any planet, far outside the familiar lanes of spacecraft and radio signals with the simple geometry of space. The solar system sits within a galaxy where stars appear close only because they are bright, and because the sky compresses depth into a flat dome. In actual distance, even the nearest stars stand so far away that the scale of everyday travel loses its meaning. The sun's planets, moons, and small bodies occupy a region that is large by human standards, yet small compared with the separation between stars. When astronomers measure those separations, they use a unit built from the speed of light, because light is the fastest known messenger, and it still needs years to cross to the nearest stellar neighbours. The nearest star system lies a little more than 4 light-years away. That number is not a flourish. It is a statement that a beam of light moving at the maximum speed permitted by known physics spends more than 4 years in transit crossing a volume where there are no roads, no fuel stations, and no air. A crude vehicle which is always slower than light inherits the same scale and must translate it into years and decades of exposure, maintenance, and survival. The solar system, by contrast, is often described in distances that light crosses in minutes or hours, and that difference alone sets the initial boundary between what is difficult and what becomes qualitatively different. The next step is to define the yardstick of the solar system itself, because leaving it is not a matter of crossing a single wall. The sun's influence fades outward in layers. Close to the sun, sunlight and the solar wind dominate, filling space with a stream of charged particles that expands in all directions. Farther out, that stream slows as it presses against the thin gas and magnetic fields that drift between stars. The region where the solar wind controls the immediate environment forms a vast bubble. Its outer boundary is not sharp, but it marks a transition inside the sun's particles shape the space weather. Outside, the surrounding interstellar medium becomes more direct. In recent decades, robotic probes travel far enough to encounter this boundary and measure changes in particle populations and magnetic conditions. Even at those great distances, those probes remain within reach because they operate without life support, accept long delays, and rely on systems designed to last without repair. Their progress highlights the first core constraint. The solar system can be crossed by machines that tolerate cold isolation and decades of slow work. A crewed mission must do the same while keeping human bodies within a narrow range of temperature, pressure, radiation dose, and psychological stability. That contrast matters even before any discussion of propulsion, because the distance itself dictates time, and time accumulates risk in a way that cannot be edited away. The scale becomes clearer when the separation between planets is set against the separation between stars. Earth orbits the Sun at a distance of about 150 million kilometers. A spacecraft can reach Mars in months depending on the chosen path and the available energy. The outer planets require years, and the farthest known dwarf planets require longer. Yet these are still distances where navigation can be updated regularly, where sunlight remains usable for some systems for part of the journey, and where communication delay remains measured in minutes to hours. Interstellar distances push those delays into years and remove the sun as a practical energy source for many technologies. Even the human habit of imagining travel as a steady cruise breaks down because a craft that aims at another star must spend much of its journey in darkness with the sun, shrinking into a bright star behind it while the destination remains a faint point ahead until very late. The geometry of distance changes not only the length of the trip, but also the nature of every decision, because choices made early must remain sound for a long time before any correction becomes possible. This leads naturally into the second basic constraint, which is the relationship between speed and time. If a vehicle travels at a modest fraction of the speed of light, the travel time to the nearest stars remains measured in decades. If it travels much slower, the travel time stretches into centuries. For human travel, a century is not a single long commute. It is longer than a typical human lifespan, longer than many institutions last, and longer than most engineered systems have ever demonstrated reliable operation without resupply or overhaul. A faster vehicle shortens time, but speed brings its own burdens. To move faster, a craft must acquire more energy, carry more propellant or access energy from elsewhere, and manage stronger stresses during acceleration and braking. The simple desire to reduce time collides with the physical cost of changing velocity. A crewed craft cannot ignore braking because arriving at a destination star system at high speed without the ability to slow down turns a voyage into a flyby. A flyby may be scientifically valuable for instruments, but for human travel it does not accomplish settlement return or sustained exploration. The need to slow down doubles the major energy demands because the craft must accelerate away from the sun and later reduce its speed by a comparable amount relative to the destination system. The distance scale converts every kilometre per second into a commitment of mass energy and engineering. At this outermost layer of the problem, before any detailed design appears, the conclusion is not a dramatic barrier, but a compounding pattern. Interstellar travel is not one hard step, it is a long multiplication of requirements. Time multiplies exposure and maintenance. Speed multiplies energy, energy multiplies mass, mass multiplies difficulty. The surrounding space adds its own steady pressures. Between the stars, matter is sparse, yet it is not absent. Hydrogen atoms, dust grains, and charged particles drift through the interstellar medium. Their density is low compared with any atmosphere, but a craft moving at high speed turns even a rare particle into an impact with significant energy. The outer scale of interstellar travel includes not just distance, but a long corridor of tenuous matter that becomes dangerous when encountered fast. That danger grows with speed, which is the very quantity needed to reduce travel time. This is another compounding relation that begins at the widest scale and follows the craft all the way inward to its skin and structure. There is also a changing radiation environment. Inside the sun's bubble, the solar wind and the heliospheric magnetic field help shape the flux of some high-energy particles from the galaxy. Outside, the craft becomes more exposed to galactic cosmic rays, which are fast-penetrating particles that pass through many materials and damage living tissue and electronics. This exposure does not depend on dramatic events. It is steady, and because distance implies long time, it accumulates. At the scale of light years, the radiation environment is not a brief hazard. It is a background condition that must be managed continuously for as long as the voyage lasts. The outer geometry of the problem also includes communication. Signals between Earth and a distant craft travel at the speed of light, so the time delay grows with distance no matter how advanced the transmitter becomes. A craft 1 light year away sends a message that arrives 1 year later. Commands sent in response arrive 1 year after that. This is not merely inconvenient, it forces autonomy. It forces systems that can detect problems, interpret them, and respond without guidance from Earth. For a crew, it also alters the social reality of the journey, because help, advice, and coordination arrive too late to function as real-time support. At the widest scale, the solar system is still close enough that mission control can participate in decisions with delays that are tolerable. Beyond it, the delay changes the structure of operations, training, repair, and safety. The outermost layer, then, is a landscape of measurements that do not yield to optimism. The nearest stars are far. The travel times at attainable speeds are long. The attempt to increase speed invokes large energy demands and introduces hazards from impacts and radiation. The delay in communication forces a level of independence that has no precedent in crewed spaceflight. These facts do not dictate that interstellar travel is impossible in principle, but they set the first frame for why it remains beyond practical human reach with known engineering. The distance is not a number on a map. It's the foundation that shapes every inner layer of the problem, from propulsion to shielding to life support to the fragile stability of the human body over long time. The journey begins with that wide emptiness, and the wide emptiness stays present in every design choice that follows. With the interstellar skull set, the next region is the solar system itself as a reference frame, because the meaning of travel changes depending on where the boundary is drawn. The solar system is not a neat disk of planets with an edge like a shoreline. It is a layered system of gravity, light, dust, gas, magnetic fields and moving particles, and its outer extent depends on which of those influences is used to define it. The most basic definition begins with gravity. The Sun holds the planets in orbit and also holds swarms of smaller bodies that range from rocky fragments to icy objects that spend most of their long paths far from the Sun. Gravity does not stop abruptly. It weakens with distance, and at great distance the pull from other stars and the overall gravity of the galaxy begins to compete. In that sense, the solar system fades into a broader gravitational environment rather than ending. Yet for practical travel, gravity alone is not enough to set a boundary, because a craft can be far from the Sun and still respond to its pull while already operating in conditions that feel interstellar. Another common way to define the solar system is by the reach of sunlight, because sunlight powers climate on planets, drives ice to sublimate on comets, and supplies energy to solar-powered spacecraft. Sunlight also fades smoothly, dropping with the square of distance. Near Earth, it is strong enough to drive larger rays. Far beyond the outer planets, it becomes so weak that power must come from stored energy, or from a compact generator. In this way, the solar system has a bright inner region and a dim outer region, and crossing from one to the other is not a single moment but a gradual loss of a resource. A third definition, often more relevant to the space environment, uses the solar wind. The solar wind is a stream of charged particles that flows outward from the Sun and carries the Sun's magnetic field into space. This flow fills the space between the planets and shapes a protective region called the heliosphere. Inside the heliosphere, the solar wind and its magnetic field influence the paths of many charged particles, and they form a changing space weather environment that can affect spacecraft electronics and human exposure during bursts from the Sun. Farther out, the solar wind expands and cools until it meets the thin gas and magnetic fields that exist between stars. That meeting does not create a wall, but it produces transitions that can be measured. The solar wind slows and becomes more turbulent, and then it yields to the interstellar medium. The interstellar medium is not empty. It contains mostly hydrogen and helium gas along with dust grains, and it carries its own magnetic field. Where the outward pressure of the solar wind balances the inward pressure of that medium, a boundary region forms. Beyond it, the craft moves in space that is shaped less by the Sun and more by the local galactic environment. Robotic probes travel far enough to sample these transitions, and their measurements show that the boundary is irregular and responsive to conditions. It can move as the solar wind changes with the Sun's activity, and as the surrounding medium varies. This makes the solar system's edge a living boundary rather than a fixed distance. For human travel, this boundary matters because it marks a shift in hazards and in resources. Inside the heliosphere, the Sun remains an active presence in particles and magnetic fields. Outside, the Sun's direct particle influence weakens, and the background of energetic particles from the galaxy becomes more dominant. The solar system also contains a reservoir of small bodies far beyond the main planets. The Kuiper belt holds many icy objects beyond Neptune, and farther still there is a more distant distribution often called the Oort cloud, a theoretical reservoir inferred from the behavior of long-period comets. These objects are important to the scale of the solar system because they extend it far beyond the last planet, and they indicate that the Sun's gravitational reach organizes matter at distances that are enormous compared with planetary orbits. Yet these distant regions are still not interstellar space in the strict environmental sense, because the heliosphere can extend beyond them in some directions and not in others, and because the transitions depend on the dynamic balance between the Sun's wind and the surrounding medium. The solar system, then, is a nested set of zones, the planetary region where sunlight is useful and where orbital mechanics can be navigated with frequent updates, then an outer region where sunlight becomes a weak trickle and travel relies on internal power, then the boundary region where the solar wind gives way and the craft's environment shifts toward the interstellar background. Establishing this yardstick makes the question of leaving more concrete. A craft that travels beyond the planets already enters a realm of deep, cold, weak light, long communication delays, and limited opportunities for correction. It does not suddenly become interstellar only when it reaches the heliosphere boundary. It progressively loses the comforts of proximity, even while it is still by some definitions within the solar system. The robotic probes that reach the outer regions demonstrate what is possible for machines. They travel for decades with modest power-limited propulsion after launch, and carefully manage systems that are designed for longevity rather than performance. They survive because they carry no fragile biology, because they can accept low data rates and long delays, and because their missions tolerate the possibility of partial failure. Those same conditions highlight why the solar system itself is a hard environment for crewed travel over long time. Even within the solar system, radiation from solar events can be hazardous. Micro impacts can damage surfaces, and small failures can cascade when resupply is impossible. A human mission beyond the planets must either carry all necessary repair capability or accept increasing vulnerability over time. The boundary region also changes the meaning of navigation. Within the planetary region, a craft can use familiar references: the Sun, the planets, their moons, and radio tracking from Earth. As it travels outward, as the angles between reference points shrink, the Sun becomes a bright point rather than a disk. The planets become difficult targets. Small errors in direction accumulate into large cross-track distances over long time, and small uncertainties in velocity become large differences in arrival conditions. The solar system as a reference frame, in other words, becomes less informative with distance. Navigation is still possible, but it becomes more dependent on precise inertial measurement, star tracking, and careful modelling of small forces. Even the pressure of sunlight can nudge a craft over years, and the release of heat can produce tiny thrusts that matter when the goal is a narrow corridor thousands of millions of kilometers away. This is still travel within the Sun's domain, yet it already resembles interstellar travel in the way small influences accumulate. Communication also changes as the craft moves outward. At the distance of the outer planets, messages require hours one way and real-time control is not possible. Operations become planned and delayed, with increasing emphasis on onboard fault detection and recovery. Beyond that, the delay becomes so long that an emergency must be handled locally or not at all. This transition happens while the craft is still in the solar system by many definitions. The yardstick, then, is not simply distance, but the loss of timely interaction with Earth and the loss of easy energy from sunlight. Defining the solar system in layers clarifies why the phrase "beyond the solar system" carries weight. It does not merely mean farther than the last planet. It means leaving the region where the Sun supplies strong energy and rapid reference, and entering a region where the environment is colder, darker, more isolated, and more dominated by steady galactic hazards. This region sets the baseline from which interstellar travel must depart, and it shows that the challenge begins long before the first light year is crossed, because the solar system's outer layers already demand endurance, autonomy, and reliability that press against the limits of human missions. The next region moves from the solar system as a spatial yardstick into the strict relationship between light travel and time, because this relationship sets a ceiling on communication and an unforgiving baseline for travel duration. The speed of light is not simply a fast speed among others. In modern physics, it functions as a limit for how fast information and energy can propagate through space. In practical terms, it sets the shortest possible time for any message or signal to cross a given distance. That means there is a minimum delay between Earth and any destination independent of technology. For crewed travel, the same limit also defines the smallest possible travel time for a craft, because no material object can be accelerated to the speed of light with finite energy according to accepted physics. A vehicle can approach that speed only by investing enormous energy, and as it approaches, each additional gain in speed costs more energy than the last. This makes the light year not just a unit of distance, but an indicator of deep constraints. A destination 4 light years away is 4 years away even for a beam of light, and longer for any ship. For human travel, the difference between years and decades is not a matter of patience. It is the difference between a mission that can be sustained with known life support durations and one that becomes an open-ended attempt to keep a small world alive for a long span. To see the scale without abstraction, it helps to anchor it in familiar solar system times. Light takes a little more than 8 minutes to travel from the Sun to Earth. It takes hours to reach the outer planets and longer to reach far beyond them. These delays already matter for operations. A spacecraft at Mars cannot be piloted like an aircraft because the delay prevents direct control. Mission planners instead send command sequences and wait for the results. Beyond the outer planets, the delay grows and the data rate drops because the signal spreads out and weakens with distance. Yet these are still delays of hours, not years. Interstellar distances stretch the same logic until it becomes a different mode of existence. A craft 1 light year away exists for practical coordination in a different time layer. If an instrument detects a problem, Earth learns of it 1 year later. If Earth proposes a fix, the fix arrives 1 year after that. If the fix fails, the news arrives another year later. This is not a situation where a distant team can guide a complex system through unfolding trouble. It is a situation where the system must function as its own caretaker. For crewed travel, this autonomy is even more demanding because the crew themselves are part of the system that can be injured or stressed, and because many critical needs require immediate response. The light-to-travel limit also shapes the emotional and organizational structure of any mission. The idea of a continual support network becomes less meaningful when support arrives after years. The mission becomes a closed society that must plan repair and decide on its own. This effect begins gradually in the solar system, where increasing delay reduces the role of immediate oversight and it becomes decisive beyond it. Time as a constraint also appears in travel duration. Suppose a craft travels at speeds achievable by the fastest probes, which are tiny compared with the speed of light. Travel to the nearest stars then requires many tens of thousands of years, which is far beyond any crewed mission. Suppose instead that a craft travels at a significant fraction of the speed of light. Even then, the time to the nearest stars is measured in decades from the perspective of Earth, and also in decades for the crew, unless the craft is so fast that relativistic time effects become substantial. Relativistic time effects, which are changes in the passage of time measured by different observers moving relative to each other, are real and well tested, but using them to shorten the crew's subjective travel time requires speeds extremely close to the speed of light. Achieving and maintaining such speeds raises energy demands into ranges that are far beyond present engineering, and it does not remove the need to protect the crew from radiation and impacts. In other words, the physics that permits time dilation also demands extreme conditions to produce it, and those conditions amplify other hazards. Time remains central. A decades-long voyage must sustain life support maintenance and mental health for a span longer than any human space mission, while operating in an environment with limited assistance and no resupply. The light travel limit further shapes what can be learned during a voyage. Navigation depends on knowing position and velocity. Within the solar system, Earth-based tracking provides precise updates and gravitational models can be refined with frequent measurement. Farther out tracking is still possible but becomes less immediate, and small uncertainties persist longer before they can be corrected. For an interstellar craft, an initial aiming error that is tiny in angle becomes a huge miss after years of travel. Corrections require propellant and time. The lag in information means that corrections must often be planned without fresh confirmation relying on onboard measurement and prediction. This again pushes toward autonomy and towards systems that can compute and act with minimal external input. Light travel time also changes the nature of scientific observation. A craft traveling to another star could transmit data, but the data arrives years after it is collected. This may be acceptable for science, but for a crew it means that outside advice about unexpected findings, hazards, or route changes arrives too late to guide immediate choices. The crew must interpret what they see and decide how to respond with the understanding that Earth's feedback is delayed by years. The craft effectively carries its own scientific institution, its own mission control, and its own emergency service because the speed of light prevents anything else. This region of the problem stays at the level of time and information before propulsion and energy are considered in detail because it sets conditions that cannot be engineered away. Faster computers do not reduce light travel time. Stronger transmitters do not reduce light travel time. Better planning does not remove the fact that events unfold far from Earth and are known only later. In the solar system, delays can be tolerated because the environment is relatively familiar and because robotic systems can be designed around delayed control. For a crew, the same delays become a structural limitation on safety because many hazards in space require immediate action, a loss of pressure, a fire, a system failure, a medical emergency. If such an emergency occurs, Earth cannot participate in its resolution in any meaningful time frame when the craft is light months away, let alone light years away. This means that the mission must be designed so that the probability of such emergencies is extremely low, and so that the crew can handle them without outside help. Achieving extremely low failure probability over decades is itself a steep demand because reliability generally decreases over time, as parts wear materials degrade and unexpected interactions occur. Time then amplifies uncertainty. The longer a system must operate, the more opportunities exist for rare failures to occur. A design that is safe for a year can be unsafe for 30 years, simply because rare events become likely when enough time passes. The light travel limit also defines a social boundary. Communication with family institutions and cultures on Earth becomes asynchronous on a scale that changes relationships. A message sent from Earth might arrive long after a situation has changed. A message sent from the craft might reach Earth when policies, resources, and priorities have shifted. The mission exists in a different tempo, and that tempo mismatch can complicate funding, support, and coordination. This is not a psychological flourish, but a consequence of time delay. Human projects rely on feedback, shared context, and timely response. Light-year delays reduce these supports, and the longer the voyage, the greater the drift between the world left behind and the world that receives the mission's communications. In this region, the primary conclusion is a quiet one. Interstellar travel is constrained not only by the need to traverse distance, but by the need to live within the time that distance imposes. A crew cannot compress time by wishing and cannot delegate urgent decisions to Earth when the messages take years. Any realistic scenario of human travel beyond the solar system must therefore begin with the acceptance that the craft and its crew become their own isolated ecosystem sustained for long duration, operating under the slow rhythm set by the speed of light. This rhythm is the outer clock that governs everything that follows inward. The next region moves inward from time and information into the mechanics of propulsion, beginning with the most basic constraint that appears when a craft must carry its own reaction mass. A rocket travels by throwing mass backward to push itself forward, and this simple principle leads to an unforgiving relationship between the craft's desired change in velocity and the amount of propellant it must carry. The core idea is that the more a rocket must change its speed, the more propellant it must expel, and because the propellant is carried at launch, adding propellant adds mass that itself must be accelerated. This creates a compounding requirement. To carry more propellant, a rocket must accelerate more mass, which requires still more propellant. In rocketry, this relation is often described as an exponential growth, meaning that requirements grow very rapidly once the mission demands a large total change in velocity. Chemical rockets, which burn fuels that release energy through chemical bonds, are powerful and well understood, and they can lift payloads from Earth and send them through the solar system. Their limitation is not a lack of thrust, but the relatively low energy per unit mass that chemical reactions provide, compared with more extreme energy sources. This translates into a limit on exhaust speed at the speed at which propellant leaves the rocket. Higher exhaust speed means that the rocket can achieve a larger change in velocity for a given fraction of propellant, while lower exhaust speed means that the rocket must spend more propellant to reach the same final speed. Chemical rockets produce exhaust speeds that are sufficient for planetary travel, but for interstellar travel, the required final speeds are so high that chemical propulsion becomes impractical because the necessary propellant mass becomes enormous. To understand why it helps to separate the journey into the key velocity changes, a crewed interstellar mission must leave Earth, escape the Sun's gravitational well to reach a high outward speed, and then later slow down relative to the destination star system. Even if the craft begins far from Earth after assembly in space, it still needs to accelerate to a high cruise speed and later decelerate. If the craft instead chooses to fly through at high speed without slowing, the mission becomes a brief passage rather than arrival. For human travel, arrival implies the ability to move within the destination system, and that requires braking. Each major velocity change costs propellant, and the cost compounds because propellant for later burns must be carried through earlier burns. In chemical propulsion, this compounding makes the mass ratio rise quickly. A mass ratio is the ratio between the initial mass of the rocket, including propellant, and the final mass after the propellant is spent. For modest missions, the ratio is manageable. For enormous velocity changes, it becomes so large that the rocket becomes mostly propellant with a tiny payload. At some point, the required propellant mass exceeds any plausible launch or assembly capacity. Even if the rocket could be built, the structural mass and engine mass would also rise, and the payload fraction would shrink further. This is not a failure of creativity, but a direct consequence of the way reaction propulsion works when the energy per kilogram of propellant is limited. Chemical rockets show this most clearly because their energy source is constrained, but the same compounding appears for any rocket that carries propellant. Increasing exhaust speed reduces the propellant burden, but achieving higher exhaust speed generally requires higher energy density, higher temperatures, or different propulsion physics, and each of these introduces engineering constraints. The rocket equation limit, therefore, is an anchor. It explains why a method that works well for reaching orbit and sending probes to planets does not scale smoothly to reaching another star with a crew and a habitable craft. The mission's demands are not just larger by a factor of 10, they are larger by factors that drive the compounding curve into a regime where carrying propellant becomes the dominant problem. There are ways to reduce the propellant requirement by using gravity assists, which are maneuvers that borrow momentum from planets. These methods are powerful for robotic missions. They allow a craft to change its trajectory and speed relative to the Sun without burning large amounts of propellant by passing near a planet and exchanging energy and momentum through gravity. Yet gravity assists are limited by the available planets and by their orbital speeds. They can add or subtract only so much velocity, and they work within the architecture of the solar system. They are helpful for reaching the outer regions and for shaping trajectories, but they cannot provide the enormous sustained acceleration needed to reach a significant fraction of the speed of light. They also do not help with braking at another star system, unless there are massive bodies there, and the craft arrives with a geometry that permits a useful exchange. For a first interstellar mission, such opportunity cannot be assumed. Another method used within the solar system is aerobraking, where a craft uses an atmosphere to slow down by drag. This is efficient because it does not require propellant, but it requires an atmosphere and a heat shield capable of handling enormous heating. For interstellar travel, aerobraking at the destination would require arriving at a planet with an atmosphere and an approach speed that does not destroy the vehicle. At the high speeds imagined for interstellar travel, the heating would be extreme. Relying on aerobraking is therefore not a general solution. It might help in a carefully chosen destination and mission profile, but it does not remove the fundamental need to manage large velocity changes with limited propellant or with some other method of momentum exchange. The rocket equation also interacts with the practical mass of life support and shielding. A crewed craft must include pressure vessels, radiation protection, thermal control systems, water, and food systems, spares, tools, and redundancy. Each kilogram added to meet these necessities increases the mass that propulsion must accelerate. In a rocket, extra mass is doubly costly because it requires more propellant, which itself adds more mass. This feedback makes it hard to add safety margins. A robotic probe can be small and accept partial failure. A crewed craft must be robust and accept very little failure. Robustness generally adds mass. In an interstellar, rocket mass adds propellant and propellant adds mass, and the cycle pushes the design toward extremes. This is why many interstellar concepts propose separating the energy source from the vehicle, such as beaming energy from afar, or using propulsion methods that do not require carrying large amounts of reaction mass. Yet before those are considered, the rocket equation provides the baseline explanation for why conventional rockets do not extend naturally to interstellar voyages. It's also why the phrase never is often used in popular discussions, because the gap between chemical propulsion and interstellar requirements is not a small engineering step. It is a jump across a region where the mathematics of carrying propellant becomes unmanageable. Even nuclear thermal rockets, which heat a propellant using nuclear energy to achieve higher exhaust speed than chemical engines, still carry propellant and still face the compounding mass ratio when the mission demands very high final speed. Nuclear thermal can improve performance for solar system travel, potentially shortening trip times to outer planets. But for interstellar speeds, even improved exhaust speed may not be enough, because the required velocity change remains enormous. Electric propulsion, which accelerates propellant ions to very high exhaust speeds using electrical power, can achieve much higher exhaust speed than chemical rockets, making it efficient in terms of propellant. Its limitation is low thrust. Low thrust means acceleration is small, so reaching high speed requires a long time of continuous operation and a large sustained power supply. For a crewed craft, long acceleration can be acceptable, but it still demands durable power systems and still requires propellant, though less. For interstellar travel, the power required to accelerate a large crewed craft to a meaningful fraction of light speed is immense, and the total energy budget becomes dominant. At this stage, the story remains focused on the carrying of propellant and the compounding mass problem, because it is the first major inward constraint after time itself. The rocket equation does not declare interstellar travel impossible. It declares that if a craft must carry its own reaction mass and relies on energy sources with limited exhaust speed, then the mass required grows so quickly that a practical vehicle becomes out of reach. It pushes interstellar planning into the realm of either extremely high energy density propulsion, extremely high exhaust speed with manageable power, or external energy and momentum sources. In this way, the rocket equation is less a single wall and more a slope that becomes steeper as the mission pushes outward in speed and duration until the slope becomes too steep to climb with known material fuels and mission architectures. The next region moves inward from the general rocket limitation into propulsion concepts that attempt to raise exhaust speed or avoid carrying all energy on board, because these concepts define what is physically imaginable and what remains practically unreachable for crewed travel. The fundamental need is to achieve a large change in velocity while keeping the craft mass within a buildable range and keeping the energy system within manageable size and safety limits. Chemical propulsion offers high thrust but limited exhaust speed. More advanced concepts aim for higher exhaust speed, which reduces propellant mass, but each step toward higher exhaust speed brings new demands in energy generation, heat, handling and material strength. Nuclear thermal propulsion uses a nuclear reactor to heat a propellant, typically hydrogen, and expel it at higher speed than chemical engines. The advantage is higher performance for a given propellant mass, potentially enabling faster trips within the solar system. The limitation is that exhaust speed, while higher than chemical, is still far below what is needed for interstellar speeds. In addition, the reactor adds mass, requires shielding for the crew, and must operate reliably for the duration of the burn. For interstellar travel, the total energy required remains enormous, and the improvement from nuclear thermal does not change the overall regime. Nuclear electric propulsion takes a different approach. A reactor generates electricity, and electric thrusters accelerate propellant to very high exhaust speeds. The propellant use is efficient, but the thrust is low, meaning acceleration is gentle. Gentle acceleration can be applied for months or years, and over long time it can build large speed changes, but only if the power system can supply continuous power, and the thrusters and power electronics can operate without failure for very long periods. For crewed travel beyond the solar system, the required power to accelerate a large habitat and a shielding mass to a significant fraction of light speed would be far beyond what compact reactors can supply with present engineering. The radiators needed to dispose of waste heat would also become enormous, because any power system that generates large electricity produces large waste heat that must be rejected to space by radiation. The result is that nuclear electric propulsion is valuable for robotic missions and for certain crewed missions within the solar system, but it does not straightforwardly scale to interstellar cruise speeds for a heavy crewed craft. Fusion propulsion is often suggested because nuclear fusion releases far more energy per unit mass than chemical reactions, and in principle it could heat propellant to very high temperatures or directly expel fusion products at high speed. In practice, controlled fusion for power production is itself a major engineering challenge on Earth, and turning fusion into a compact, reliable rocket engine adds further complexity. A fusion engine would need to confine hot plasma, manage intense neutron radiation for many fusion fuel cycles, and convert fusion energy into directed exhaust without destroying its own structure. For a crewed craft, it would also need to operate safely for long periods with minimal maintenance. Even if these challenges were solved, a fusion rocket still faces the need to carry reaction mass or fuel, and for interstellar missions the fuel and shielding requirements could remain very large. The main attraction is that a high exhaust speed reduces the propellant fraction, but the practical obstacles include building a reactor that works as a propulsion system supplying and storing the fuel, and ensuring the engine can start, stop and operate over years without failure. Antimatter propulsion represents an even higher energy density because matter and antimatter annihilate to produce energy with extremely high efficiency. In principle, this could enable very high exhaust speeds and high performance. In practice, antimatter is exceedingly difficult to produce in large quantities, expensive in energy terms, and difficult to store safely. Antimatter must be held away from normal matter using electromagnetic traps, and any failure of containment leads to annihilation and radiation. Storing even small amounts requires complex systems and extreme reliability. Using antimatter for crude propulsion would also create radiation fields that need shielding, adding mass. This concept, while physically grounded, currently lies far beyond practical engineering and manufacturing capacity. Because carrying energy and propellant on board becomes so demanding, many interstellar ideas shift toward external energy sources. Beamed energy propulsion is one approach. In this concept, a powerful laser or microwave beam from the solar system pushes a sail attached to the craft. The craft carries little or no propellant for acceleration, reducing mass. The energy source remains near Earth or near the Sun, where it can be large, serviced and supplied. The sail converts photon momentum into thrust, which is small but continuous. For a small probe, such a system could in principle achieve high speeds. For a crewed craft, the sail must be enormous. The beam must be extremely powerful and precisely aimed over long distances, and the craft must remain stable in the beam without tearing or overheating. The beam also spreads with distance due to diffraction, requiring very large optics to keep it focused. Even if the optics are built, maintaining alignment over millions and then billions of kilometers requires extraordinary pointing control. There is also the issue of deceleration. A beamed sail can accelerate outward, but slowing down at the destination requires either another beam source at the far end or an onboard method of braking. Without braking, the craft arrives at the destination star system still moving too fast to stop. One proposed method for braking is to use a magnetic sail that interacts with the interstellar medium or the destination star's wind, but the effectiveness depends on uncertain plasma conditions and would require a large structure. For crewed travel, relying on such braking adds risk and complexity. Another external method is to use the sun itself as an energy and momentum source. Solar sails use sunlight pressure, which is weaker than a laser beam but always present near the sun. A sail can spiral inward toward the sun and then use the strong sunlight pressure near perihelion to gain speed outward. This can achieve higher speeds than conventional propulsion for certain payloads, especially small ones. For a crewed craft, the sail area and structural demands become very large, and operating close to the sun introduces thermal risks. Even then, the maximum speed achievable remains limited, and braking remains a problem. All of these concepts reveal a consistent pattern. To reach another star in a human timescale, the craft must either achieve very high speed or find a way to reduce the perceived time. High speed demands high energy. High energy demands either carrying powerful energy sources on board or building large external infrastructure. Carrying the energy source requires shielding, heat rejection, and long-term reliability. External infrastructure requires building massive beam systems, optics, power supplies, and guidance systems that can operate for years with extreme precision. Both approaches are far beyond current large-scale space engineering. The solar system has not yet demonstrated construction and maintenance of structures on the scale that a beamed propulsion system for crew would require. Even within Earth orbit, maintaining large stations and shown lifetimes involves continual resupply and repair. A beaming array or a sail system scaled for humans would demand industrial capacity and space-stable long-term governance and a sustained economic reason to keep it working, because a failure years into acceleration could strand a craft without the ability to complete its mission. In this region, the difficulty is not a single missing invention, but a stack of requirements. A propulsion system for interstellar crewed travel must produce enormous total energy, direct it efficiently into a useful thrust, keep the crew protected from radiation and heat, and operate with reliability measured not in hours or months but in years and decades. It must also provide a method of stopping at the destination which is often as hard as leaving. The concepts that seem to avoid the rocket propellant burden tend to shift the burden into infrastructure and precision. The concepts that carry energy on board tend to shift the burden into mass shielding, heat management, and reactor complexity. These burdens are not theoretical impossibilities. They are practical mountains in engineering, manufacturing, and long-duration operations. They explain why, even though interstellar travel is often discussed, the path from present capabilities to a crewed ship beyond the solar system remains blocked by the scale of propulsion demands and by the need to solve acceleration and deceleration with systems that can endure. The next region moves inward from propulsion concepts into the physical experience of acceleration and the limits set by human tolerance and by structural demands on a spacecraft. A craft that travels to another star in a humanly meaningful time must either travel extremely fast or sustain acceleration for a long period. Sustained acceleration has an appealing simplicity. If a craft can accelerate at a level similar to Earth's gravity for a year, it can reach a very high speed. It can then flip and decelerate for another year and arrive at the destination with manageable relative speed. In this simplified picture, the crew experiences a steady artificial gravity from acceleration, which could reduce some health problems associated with weightlessness. Yet the simplicity hides the scale of the required energy and the engineering challenges. Even a fraction of Earth gravity maintained for months requires enormous thrust if the craft is massive, and crewed craft are massive because they carry shielding, life support, and redundancy. The thrust requirement ties back to propulsion. High thrust usually means expelling large amounts of propellant quickly or producing powerful external pressure on a sail. If the craft uses a rocket, high thrust demands a high propellant flow and a powerful engine. If it uses beamed energy on a sail, high thrust demands an intense beam and a sail that can tolerate high flux without degradation. The human tolerance question also has practical boundaries. Humans can tolerate one Earth gravity continuously because it is the condition of life on Earth. Higher sustained acceleration becomes stressful, especially for long periods, because the cardiovascular system must push blood against greater forces and tissues and organs experience increased loading. Short bursts of higher acceleration can be tolerated depending on direction and training, but long-duration exposure is limited. For interstellar travel, a sustained acceleration near one Earth gravity is likely the upper comfortable bound, and many mission concepts would require lower acceleration to reduce power and structural demands. Lower acceleration lengthens the time to reach high speed, increasing exposure to radiation and the duration of mission systems. This trade-off is a central constraint. If acceleration is high, propulsion becomes harder. If acceleration is low, time becomes harder. There is no regime where both are easy. Structural demands grow with acceleration and with the need to withstand long periods of thrust. A spacecraft under thrust experiences forces through its frame as mass resists acceleration. The habitat shielding tanks and engines must be connected by structures that transmit these forces without fatigue failure. Fatigue is the gradual weakening of materials under repeated or sustained stress, often accelerated by vibrations and temperature cycles. In a long mission, materials are also exposed to radiation and micrometeoroid impacts, which can create microcracks and weaken structure. A craft designed for decades must not only be strong, but also resistant to long-term degradation. High acceleration increases the stress on joints, welds, bolts, and composite interfaces. It also complicates internal layout because liquids and gases behave differently under acceleration, and tanks and plumbing must handle pressure and flow in a moving gravitational field. Even at one Earth gravity, maintaining acceleration for months turns the spacecraft into a constantly loaded structure, more like a long bridge that must never crack than like a short-duration launch vehicle that completes its burn in minutes. The direction of acceleration matters for the crew's body. If the craft accelerates along the axis from head to feet, it mimics Earth gravity and is more tolerable. If it accelerates in other directions, blood shifts and discomfort become more severe. This suggests a craft design with a consistent thrust axis aligned with the living deck. Yet this alignment has consequences for engines, radiators, shielding, and the placement of mass. In addition, the craft may need to rotate or reorient at mid-course to switch from acceleration to deceleration. This maneuver, often imagined as a flip, requires attitude control and structural considerations, especially if large sails or radiators are present. Large flexible structures can be difficult to rotate without inducing oscillations, and managing those oscillations over a long mission requires control systems and structural damping. The human aspect also includes the effects of long-duration confinement and the need for medical stability. Even if acceleration provides artificial gravity, the crew remains inside a closed habitat with limited medical resources. A steady gravity may reduce bone loss and muscle atrophy compared with weightlessness, but it does not remove all physiological risks. Long missions pose challenges in immune function, exposure to chronic radiation, and the cumulative probability of illness or injury. Acceleration does not directly solve these problems, and it can add others such as motion sickness during changes in thrust or orientation. Designing a mission around steady acceleration also implies that the propulsion system is reliable enough to operate continuously. Any interruption in acceleration changes the internal gravity environment and can disrupt systems that depend on it. More importantly, an interruption suggests a failure, and in interstellar space, failure must be handled locally. The propulsion system becomes a life support system in its own right, because it defines not only trajectory but also potentially the gravity environment. This increases the required reliability. Human tolerance is also influenced by vibration and noise. High-thrust engines can produce vibration through pumps, combustion, or plasma processes and mechanical structures. Vibrations can fatigue materials and affect sensitive equipment. For a crew, chronic vibration can disturb sleep and increase stress. The requirement for calm, stable living conditions pushes designers towards smooth, controlled thrust, which can conflict with some propulsion methods. Electric propulsion tends to provide smooth thrust but low acceleration. Chemical propulsion provides high acceleration but in shorter bursts and with intense mechanical activity. Nuclear and fusion concepts vary, but all must manage mechanical and thermal stresses. The acceleration discussion also forces attention on mass distribution. To accelerate efficiently, the craft must control its center of mass relative to thrust. As propellant is consumed, mass shifts, and the craft must compensate to keep thrust aligned. Misalignment produces torque and can induce unwanted rotation, requiring attitude control and consuming additional propellant or reaction mass. For long missions, even small inefficiencies matter. The relationship between acceleration and mass ties back into the rocket equation. High acceleration is easier with higher thrust, but higher thrust often means higher propellant flow, which increases propellant mass and makes the craft heavier. The heavier craft then needs more thrust for the same acceleration. This again reveals a compounding loop. Even a conceptual design that assumes steady one-Earth gravity acceleration quickly runs into the fact that the energy required to accelerate a large mass to a significant fraction of light speed is vast. Energy scales with the square of speed in classical terms and becomes even more demanding as relativistic effects appear. The energy must come from somewhere, and it must be converted into directed motion with waste heat managed and crew protected. The acceleration region, therefore, is a bridge between propulsion and biology. It shows that even if a propulsion method exists in principle, the mission must choose an acceleration profile that humans can tolerate and that structures can endure. If the profile is aggressive, structural and energy requirements explode. If it is gentle, travel time lengthens, making life support and radiation challenges more severe. In this way, acceleration does not offer a free pathway to human interstellar travel. It is another layer where fundamental physics and human limits intersect. The crew cannot be treated as a payload that can be shocked, frozen or neglected. They must remain healthy and functional. The craft cannot be treated as a disposable stage. It must endure as a home and a machine for a long span. Sustained acceleration brings these demands into continuous contact, and it explains why many practical discussions of human travel beyond the solar system return to the same conclusion: the journey is not blocked by a single missing engine, but by the combined requirements of energy, reliability, structural endurance, and the narrow tolerances of the human body. The next region moves inward from acceleration into the sustained supply of energy over decades, because propulsion is only one part of the power problem. A crewed craft traveling far from the sun must support life, maintain temperature and pressure run. Computers and sensors operate communication systems and perform repairs and manufacturing tasks. These needs persist whether or not the craft is accelerating. In deep space, sunlight is weak and becomes negligible as a practical primary source beyond the outer solar system for a large habitat. Even within the outer solar system, solar power requires very large arrays and careful pointing, and their mass and vulnerability become concerns. For a mission beyond the solar system, the craft must rely on internal energy sources that can operate reliably for very long spans. The most realistic internal sources are nuclear in some form, because nuclear energy provides high energy density and does not depend on external supply. Yet nuclear systems introduce their own constraints, including radiation shielding, heat management, fuel longevity, and the complexity of long-term operation without resupply. A power system for an interstellar crewed craft must deliver continuous electricity and heat control while also supporting the propulsion system if the propulsion uses electric power. It must do this for years and perhaps decades. Reliability becomes the central requirement. In short, systems can be built with some redundancy and can be repaired with spare parts. In long missions, redundancy and spares must cover not only anticipated failures but also rare ones that become likely over time. A simple way to see this is to think in probabilities. A component with a 1 in 1,000 chance of failure per year might be acceptable for a 1-year mission. Over 30 years, that same component has a much higher cumulative probability of failing at least once. To keep the overall system reliable, either the component's failure rate must be dramatically lower, or the system must have multiple independent backups, or the crew must be able to repair or replace it with materials and tools carried on board. Each of these solutions adds mass and complexity. Mass and complexity then feed back into the propulsion and shielding requirements. The energy system must therefore be both powerful and simple enough to be maintainable. This is a difficult combination. Nuclear reactors used on Earth rely on large infrastructures, extensive monitoring and regular maintenance. Space reactors must be more compact, must operate under microgravity or variable gravity conditions, and must be resistant to vibration, radiation damage and thermal cycling. They must also be safe because a serious failure could release radiation or heat that threatens the crew. Shielding is required to protect the crew from the reactor's radiation, especially neutrons and gamma rays. Shielding adds mass. Placing the reactor far from the habitat can reduce shielding needs, but distance requires long power transmission lines and structural booms which add mass and introduce failure points. A common approach is to place the reactor at the end of a long truss with the habitat at the other end and to use the craft's geometry as part of the protection. This helps, but it creates a long structure that must endure acceleration loads, impacts and thermal expansion. It also complicates attitude control. In addition, radiators used to dump waste heat must have large surface area and must be placed where they can radiate to cold space without being overheated by the reactor or by other parts of the craft. Radiators are also vulnerable to micrometeoroid and dust impacts. Over decades, small punctures can reduce performance. A power system that depends on delicate radiator surfaces must include redundancy repair strategies or self-sealing designs. All of these add complexity. Long-duration fuel supply is another constraint. A reactor's fuel is consumed gradually. The reactor must be designed with enough fuel to last for the mission duration with a safety margin. It must also handle changes in fuel composition and reactor behavior over time. Materials in the reactor core are bombarded by neutrons and other particles which can make them brittle or cause swelling. Coolant systems can corrode. Control mechanisms can degrade. On Earth, reactors are inspected and maintained. In deep space, inspections are limited and replacements must be carried. Some reactor designs may be more robust, but the basic problem remains decades of operation in an unforgiving environment without external support is a severe requirement. Radioisotope power systems which use the heat from radioactive decay to generate electricity are highly reliable and have been used in deep space probes. Their limitation is low power. They can run instruments and computers, but they cannot power large habitats or high-power propulsion. They also rely on scarce isotopes and still produce waste heat that must be managed. For a crewed craft, radioisotope systems might be useful as backups, but they cannot supply the main power. If the mission aims for high speed, and especially if it relies on electric propulsion, the power levels required become very large. High power in space means high heat production, because no power conversion is perfect. Any inefficiency becomes heat. Even if the propulsion uses a high efficiency method, the total power involved is so large that the waste heat becomes a major design driver. In space, heat cannot be carried away by air or water outside the craft. The only way to reject heat is by thermal radiation. Radiators must be large enough that they can emit the waste heat at a temperature that does not overheat the system. If radiators are too small, they must run hotter to radiate the same amount of power, which can exceed material limits and reduce reliability. Larger radiators add mass and present larger targets for impacts. This creates another trade-off to support high power. The craft must either accept very large radiator structures or accept high operating temperatures that challenge materials and long-term stability. The energy system also interacts with the life support system. Life support includes air circulation, carbon dioxide removal, oxygen, generation water, recycling, waste processing, and food storage or production. Many of these processes require electricity and heat. In addition, the habitat must maintain a stable internal temperature. In deep space, the environment is cold, but that does not mean the habitat naturally stays cold. Internal electronics, people and machinery generate heat continuously. The craft must both distribute heat evenly and remove excess heat. The energy system becomes the heart that not only powers devices, but also manages thermal balance. If power generation fails, life support fails. If thermal control fails, life support fails. This coupling increases the need for redundancy and for systems that degrade gracefully rather than failing suddenly. A decades-long mission also faces the challenge of storing energy for emergencies. Even with a reactor, the craft may need batteries or other storage to handle short-term peaks to restart systems or to supply power during maintenance. Energy storage systems degrade over time. Batteries lose capacity. Mechanical systems wear. Any storage method must be sized with long-term degradation in mind. It must also be safe, because failures in energy storage can cause fires or toxic releases hazards that are especially dangerous in a closed habitat. Repair capability becomes central. A crewed craft cannot depend on every component lasting decades without failure. Instead, it must be able to replace components, seal leaks, patch radiators, and perhaps even fabricate parts. This implies carrying tools, raw materials, and detailed knowledge. It also implies crew time devoted to maintenance. Crew time is limited, and long-term maintenance burdens can compete with health, rest, and mission operations. The power system must therefore be designed not only for performance but for maintainability modules that can be replaced, accessible connections, and diagnostic systems that can isolate faults. Each maintainability feature adds mass and complexity. In this region, the problem of human interstellar travel becomes less about a single engine and more about building a durable, self-sustaining industrial ecosystem in a small volume. The craft must generate power, manage heat, protect its inhabitants, and keep its machinery functioning for a span that exceeds typical engineering lifetimes. The solar system offers no rescue if the craft is far beyond it. Even within the solar system, rescue is difficult. Beyond it, rescue is effectively absent. The energy system must therefore be more reliable than any system humans currently operate in isolation for decades. It must also function in the face of cumulative damage from radiation and impacts. When this reality is combined with the propulsion demands, it becomes clear why human travel beyond the solar system remains out of reach. The energy problem is not merely generating enough power to go fast. It is generating, controlling, and sustaining power in a way that keeps a fragile life support bubble stable for a very long time, with no external help while the craft moves through a hazardous environment. The next region moves inward from energy supply into thermal control because in deep space, heat is both a resource and a threat, and managing it becomes one of the most persistent engineering requirements. Inside a crewed spacecraft, heat is produced continuously. People produce heat by metabolism. Electronics produce heat whenever they operate. Power systems and propulsion systems produce heat through inefficiency, because no conversion of energy into useful work is perfect. Even life support processes such as compressing gases or running pumps add heat. On Earth, heat can be carried away by air and water, and can be released through convection and evaporation. In space, there is no surrounding air. There is no external fluid to absorb heat. The only way a spacecraft can lose heat to its environment is by radiation, which is the emission of infrared energy from surfaces into space. This makes thermal control a surface area problem. The more heat a craft must reject, the more radiating area it needs, or the hotter its radiating surfaces must be. Both options have consequences. A radiating surface that runs hotter can emit more heat per unit area, but high temperature stresses materials, increases thermal expansion, and can degrade coatings and joints over time. A larger radiating surface can run cooler, but it adds mass, increases complexity, and becomes more vulnerable to impacts. Thermal control also involves distributing heat. Inside a habitat, temperature must be stable and comfortable, and sensitive equipment must be kept within operating ranges. Heat must be moved from where it is generated to where it can be radiated away. This requires heat exchangers, pumps, pipes, and radiators. These systems must operate continuously for years. They must be designed to avoid leaks, clogs, and freezing. They must also function in different gravity conditions if the craft alternates between acceleration and coasting. In a microgravity environment, fluids behave differently. Bubbles do not rise. Liquids can form films and globules. Pumps and separators must be designed accordingly. Long-duration missions also face the problem of material degradation. Coolant fluids can change properties, absorb gases, or degrade under radiation. Pipes can corrode, seals can harden. A small leak in a coolant loop can be manageable in a short mission, but in a decades-long mission, any leak is a slow drain on the craft's ability to manage heat. This makes leak detection and repair a central requirement. Thermal control is also tied to the external environment. In the inner solar system, sunlight is strong and can heat surfaces. Spacecraft use reflective coating sunshades and radiators oriented away from the sun to manage this. In the outer solar system and beyond, sunlight becomes weak, which reduces external heating, but it does not remove thermal challenges. The craft still produces internal heat. In fact, deep space makes heat rejection harder in one sense, because the craft must maintain some systems above freezing, while also rejecting waste heat. This is a balance. Some parts of the craft, such as fuel lines, water systems, or batteries, may need to be kept warm. Other parts, such as high-power electronics, must be kept cool. The craft must route heat intentionally, sometimes using heat as a resource to keep systems warm, while still ensuring that excess heat is radiated away. This creates a complex thermal network that must remain stable across many years. If the craft relies on a reactor, thermal control becomes even more demanding. A reactor produces large heat, and even if most is converted to electricity, the remainder must be rejected. The conversion process itself, whether it uses turbines or thermoelectric elements or other methods, produces waste heat. High-power propulsion systems such as electric thrusters also generate heat in power electronics and in the thrusters themselves. Radiators must handle this load. Radiators are typically large panels with internal coolant channels. They must remain sealed. They must maintain structural integrity. They must endure temperature cycling as the craft changes orientation or power level. Over decades, repeated thermal cycling can fatigue materials. Expansion and contraction can loosen joints. Coatings can crack. In addition, radiators must survive impacts from micrometeoroids and dust. Even small holes can allow coolant to escape. Some designs consider using many small radiator segments so that damage to one does not disable the entire system. This increases redundancy but also increases plumbing complexity. Complexity increases the chance of failure. The thermal problem is therefore a network of trade-offs rather than a single design choice. Thermal control also influences shielding and hull design. A thick radiation shield can insulate the habitat, reducing heat loss, which can be helpful in deep cold. But insulation can also trap unwanted heat, making it harder to reject waste heat. A habitat that is too well insulated may overheat unless heat is actively moved to radiators. Conversely, radiators must be placed outside shields, which can create thermal gradients and structural interfaces that must remain tight. If the craft uses water as radiation shielding, water can serve as a heat capacity buffer as well. It can absorb heat and distribute it. But keeping water in the right place for shielding and heat control requires careful tank design and management. Any use of water for multiple functions ties systems together, and coupled systems can fail in cascades. The thermal environment also affects the crew. Humans are sensitive to temperature and humidity. In a closed habitat, air must be circulated and to prevent hotspots to remove carbon dioxide and to control moisture. Moisture control is important because condensation can form on cold surfaces, leading to corrosion and biological growth. Managing humidity requires dehumidifiers and heat exchangers which consume power and add complexity. In microgravity, condensation behavior differs, and water can cling to surfaces, creating contamination and electrical hazards. A long mission must keep these processes stable with filters that can be replaced and ducts that can be cleaned. The thermal control system must be quiet and steady to support rest and robust enough to handle variations in crew activity, equipment operation and power generation. Over decades, the challenge is not achieving a thermal balance once. It is maintaining that balance through component aging, through unplanned changes, and through damage. The outside environment introduces another subtlety. As a craft travels through interstellar space, it encounters sparse gas and dust. At high speeds, impacts deposit energy into the craft's forward surfaces, which becomes heat. The heat load from these impacts depends on speed and on the density of the medium. Even if the density is low at high speed, the energy per impact becomes large. Over long time, the cumulative heating and damage to forward surfaces can affect thermal properties. Coatings can erode, surfaces can become rough. Radiative emissivity, which is the ability of a surface to emit heat, can change. A surface that becomes damaged may radiate differently, altering thermal balance. The craft must therefore consider not only its initial thermal design, but how that design evolves under bombardment. In the solar system, spacecraft already account for degradation of coatings and solar arrays due to radiation and micrometeoroids. Over decades in interstellar space, this degradation becomes more significant. This region also includes the need to keep some systems cold. Certain sensors and instruments perform better at low temperatures. Some power conversion systems may require temperature gradients, yet in a crude habitat, temperatures must remain moderate. Maintaining cold zones requires insulation and sometimes active cooling, which consumes power. If the craft is far from the sun, it might seem that cooling is easy because the outside is cold. In reality, without convection, cooling still requires moving heat to a radiator. The coldness of space is not a sink that absorbs heat directly. It is the absence of incoming heat. The craft must still radiate its heat away. This is a critical conceptual point because it shows that deep space does not automatically solve heat problems. It changes them. It makes some external heating less severe, but it makes the craft's internal heat management fully dependent on its own radiative systems. In this region, thermal control becomes a quiet but dominant requirement that runs through every other system. Power generation creates heat. Life support creates heat and moisture. Electronics create heat. Shielding affects insulation and heat flow. Radiators must endure damage. Plumbing must remain sealed. Maintaining a habitable temperature over decades is not a passive feature but an active continual operation. When combined with the need for high power and long-duration reliability, thermal control becomes one of the reasons human travel beyond the solar system remains impractical. The craft must not only go far and fast, it must also remain thermally stable as a sealed world, radiating its waste heat into the dark for as long as the journey lasts. The next region moves inward from heat into the radiation environment beyond the heliosphere, because radiation is one of the most persistent hazards for both biology and electronics, and it grows more challenging as time and distance increase. Space radiation comes in several forms. There are energetic particles from the Sun, including bursts associated with shear flares and coronal mass ejections. There are also galactic cosmic rays, which are high-energy particles that originate outside the solar system, accelerated by energetic processes such as supernova remnants and other astrophysical sources. Cosmic rays include protons, heavier nuclei, and a small fraction of electrons and other particles. Their energies can be so high that they penetrate deeply into materials, and when they strike shielding, they can produce secondary radiation, including neutrons that also contributes to dose. Within the heliosphere, the solar wind and the sun's magnetic field modulate the intensity of some cosmic rays, reducing their flux at certain energies compared with interstellar space. The heliosphere does not block cosmic rays entirely, but it shapes the spectrum and intensity. Beyond the heliosphere, the craft is more directly exposed to the local interstellar environment, and galactic cosmic rays become a steady background. The solar particle events still exist, but their intensity at the craft depends on distance and magnetic connection to the Sun. In interstellar space, the dominant concern for long-duration exposure becomes galactic cosmic rays because they are persistent and because their high energies make them difficult to shield. For a crewed mission lasting decades, dose accumulates. Radiation dose is measured as energy deposited in tissue and its biological effect. It matters not only how much dose is received, but also what kind of radiation delivers it. High-energy, heavy ions, which are a component of cosmic rays, can cause dense ionization tracks through cells, producing complex DNA damage that is harder for cellular repair mechanisms to handle. This type of damage increases cancer risk and can also affect the nervous system and cardiovascular system. The scientific understanding of these risks is based on a combination of radiation biology, epidemiology, and data from astronauts and other exposed populations. There are uncertainties, especially for long-duration exposure to the exact cosmic ray environment in deep space, but the broad conclusion is clear. Chronic exposure at levels expected beyond Earth's magnetic protection increases health risks, and for decades-long missions, the accumulated risk becomes large. Radiation also affects electronics. Energetic particles can cause single-event effects, where a particle passing through a microchip flips a bit or triggers a transient current. In more severe cases, it can cause latch-up damaging components. Over time, radiation can degrade semiconductor materials and optical components. Electronics can be hardened by design, using materials and architectures that are more resistant, and systems can include redundancy and error correction. Yet hardening often increases mass power use and complexity. Over decades, the probability of cumulative damage increases. A crewed craft must keep its electronics functioning for navigation, life support, control power, management, and communication. Failures in these systems are not mere inconveniences, they can become life-threatening. Therefore, radiation protection is not only about shielding the crew, it is also about maintaining the craft's technological nervous system. Shielding for radiation begins with material. Dense materials like metals can stop some forms of radiation, but for high-energy particles, especially heavy ions, dense material can produce secondary particles when struck. Hydrogen-rich materials such as water or plastics can be more effective per unit mass for reducing dose from galactic cosmic rays because they slow and fragment incoming particles with fewer high-energy secondaries. This is why water is often considered a useful shielding material. A crewed craft already carries water for life support. Placing water tanks around the habitat can provide some protection. Food supplies and other consumables can also be arranged as shielding. Yet for long missions, consumables are used and their distribution changes, which can alter shielding over time. A craft designed for decades must manage this, perhaps by maintaining a dedicated shielding layer that is not consumed, or by replenishing shielding with recycled materials. Any dedicated shielding adds mass. Mass adds propulsion cost and structural demands. There is also the question of how much shielding is enough. For solar particle events which can deliver high dose over short-time shielding, can be effective if the crew can retreat to a storm shelter, a small region with extra shielding during an event. This approach reduces the mass of the shielding required for the entire habitat. It relies on early warning and on the ability to predict or detect events. In interstellar space, solar particle events from the Sun become less relevant as distance increases, but other stars can have their own particle events, and the craft may still be exposed to occasional energetic particle bursts from various sources. However, the most persistent background is galactic cosmic rays, which cannot be avoided by timing and which penetrate deeply. For cosmic rays, a storm shelter is less effective because the exposure is continuous. A heavy shelter can reduce dose while the crew is inside, but the crew cannot remain in a small shelter for years. Therefore, the overall habitat must include a baseline shielding level. The required thickness to reduce cosmic ray dose substantially can be large, potentially many tens of centimeters of water equivalent depending on design goals. This translates into many tons of mass for a modest habitat volume. A craft carrying such mass faces propulsion and structural penalties. There is also a diminishing returns effect. Adding more shielding reduces dose, but beyond a certain point the reduction per added mass becomes smaller, and secondary particle production can complicate the benefit. This makes the optimization difficult. It is not simply a matter of adding an arbitrarily thick wall. In addition to shielding, mission designers consider operational strategies such as choosing trajectories and timing to reduce exposure, or using magnetic or electrostatic shielding concepts that attempt to deflect charged particles. Magnetic shielding would create a field around the habitat similar in concept to Earth's magnetic field to bend particle paths. In practice, generating a strong enough field over a large volume requires massive magnets and substantial power, and it introduces hazards such as strong field effects on equipment and on crew. Superconducting magnets could reduce power losses, but they require cryogenic systems to keep them cold, which adds complexity and more heat management. Electrostatic shielding would use electric fields, but the voltages required and the risk of arcing and plasma interactions make it challenging. Both concepts are areas of research and conceptual study, but neither is demonstrated at the scale needed for a crude interstellar craft. The radiation problem therefore returns to mass and to time. The longer the voyage, the more dose accumulates. The farther from the Sun and Earth, the less protection exists from magnetic fields. The more shielding is added, the heavier the craft becomes, making propulsion harder. The need for shielding also influences habitat design. Crew sleeping areas can be placed deeper within the mass of the craft, surrounded by water tanks and supplies. Work areas can be arranged to keep exposure lower during long periods. Yet the crew must still perform maintenance and operations in less protected zones at times. Long missions may also require exercise areas, medical areas, and potentially food production areas, all of which must be shielded. Shielding must also consider the directionality of radiation. Cosmic rays come from all directions, though their distribution can be slightly anisotropic depending on local conditions. This means shielding must be relatively uniform to avoid weak spots. Uniform shielding adds mass in all directions, which is expensive. Directional shielding can be used if the craft's orientation is stable, but over long missions, orientation changes may be needed for navigation, communication, or thermal control. A design that assumes a permanent shielded direction may conflict with these operational needs. Radiation also interacts with materials. Polymers can degrade under radiation. Metals can become embrittled. Optical coatings can darken. Over decades, the structure of the craft may change as radiation breaks chemical bonds and creates defects. This affects not only shielding but also seals, wiring, insulation, and mechanical parts. The craft must choose materials that can withstand long exposure or be prepared to replace them. Replacing structural materials is difficult. Therefore, material selection becomes a radiation design choice as well. In this region, radiation is not treated as a dramatic event but as a slow pressure. It accumulates in the bodies of the crew and in the components of the craft. It forces the design to carry mass and to accept complexity and protection. It increases the need for redundancy in electronics and for careful habitat layout. It reinforces the earlier conclusion that time is the enemy, because time turns a manageable background into a major health and reliability risk. For travel beyond the solar system, where travel times to the nearest stars are long, radiation becomes one of the strongest reasons that crewed missions remain impractical with current technology. The journey is long enough that dose becomes significant, and the shielding needed to reduce it becomes heavy enough to deepen every other challenge. The next region moves inward from the broad radiation environment into shielding as a physical design problem, because protection is not only a matter of thickness, but also of how mass materials, geometry, and mission operations interact over long time. A crewed spacecraft is limited by how much mass it can accelerate, and by how reliably it can carry that mass without degradation. Radiation shielding competes with every other mass demand, yet it also supports every other demand by preserving crew health and keeping electronics functional. This makes shielding a structural element of the mission, not a simple add-on. The most effective shielding approach is often to use materials already needed for other purposes, such as water, food, and waste, placing them strategically so that they protect the habitat while still performing their primary functions. Water is especially useful because it is hydrogen-rich and dense enough to provide substantial attenuation of many particle energies. A habitat surrounded by water tanks can reduce radiation dose and also provide a buffer for thermal control because water can absorb heat. Yet a long mission complicates this because water is constantly cycled. It is used for drinking, hygiene, oxygen generation, and other processes, and it is recovered from waste. This means the water is not a static wall. It is a working fluid. Keeping it positioned as shielding requires a tank architecture that maintains water distribution even as it moves through life support loops. One approach is to have a dedicated water shielding layer, where water volume is maintained, while separate working water loops draw from and return to that reservoir. This stabilizes shielding, but adds plumbing and tank complexity. Another approach is to design a storm shelter, a smaller region within the craft where the shielding is thicker, using concentrated water and supplies. This works well for solar particle events, but for galactic cosmic rays it only helps during the time that the crew spends inside. Over a decades-long mission, the crew must live and work in the larger habitat, so the baseline shielding of the whole habitat still matters. Food and other consumables can also be used as shielding. Packed food, spare parts, and stored materials can be placed around sleeping quarters and work areas. Yet consumables are gradually used. If food is stored as shielding in the early years, by the later years, the mass may be reduced and shielding weakened. This can be managed by using waste as replacement shielding. Waste includes organic waste packaging and other materials that can be processed into stable bricks or panels. In principle, waste can be compacted and positioned to maintain shielding as consumables are used. This requires processing equipment and storage volume. It also requires careful control to avoid contamination and odor, and it must ensure that waste does not become a biological hazard. The shielding system becomes part of the life support and logistics system. The craft must treat mass not as something consumed and lost, but as something that changes form and location while remaining part of the protective envelope. This is possible in principle, but it is complex, and complexity can fail. Material choice matters because high-energy radiation interacts differently with different elements. Dense metals like lead are good for blocking gamma rays, but for charged particle radiation typical of cosmic rays, dense materials can generate secondary showers when struck by energetic ions producing neutrons and other particles that can penetrate and add to dose. Hydrogen-rich materials tend to moderate and fragment particles with fewer harmful secondaries per unit mass. Plastics such as polyethylene are often discussed for this reason. Water, which is also hydrogen-rich, performs similarly. Yet plastics can degrade under radiation and water tanks can leak. Metals are strong and useful structurally, so most spacecraft use metal hulls. The challenge is to combine structural strength with radiation protection without creating an unmanageably heavy craft. A common design concept is a layered structure, an outer micrometeoroid shield to protect against impacts, a structural hull to maintain pressure, and inner layers of hydrogen, rich shielding around critical areas. The thickness of each layer is constrained by mass and by the need to allow access for maintenance. Shielding that cannot be inspected or repaired can become a hidden failure point. Over decades, small impacts can erode outer layers and expose inner layers. The craft must be able to detect degradation and respond. Geometry is another key factor. Radiation arrives from many directions, but not all directions are equal. If the craft is accelerating or if it has large structures like engines, propellant tanks, or radiators that already add mass in certain directions. If the craft has a heavy propulsion module at one end, that mass can provide some shielding from that direction. Placing the habitat behind the propellant tanks relative to the expected radiation direction can reduce dose for particles arriving from that side. However, cosmic rays are largely isotropic and relying on directional shielding leaves vulnerabilities. Still, arranging heavy masses to provide partial shielding can reduce the total dedicated shielding needed. This kind of mass budgeting is central to spacecraft design, yet it also interacts with thermal control and propulsion. Propellant tanks may need to be kept within certain temperatures. Engines may produce heat and radiation. Placing the habitat too close to the propulsion module can increase exposure to engine-related radiation or heat. Placing it farther away reduces that exposure but increases structural length and mass. The craft must also consider shielding for electronics. Some electronics can be placed inside the habitat benefiting from the same shielding. Others must be outside, such as sensors and antennas. External electronics need their own hardened enclosures. Antennas must have a clear line of sight for communication, which can limit shielding placement. If communication requires pointing a dish toward Earth, then the craft's orientation and the location of the dish relative to shielding become a design constraint. Over decades, the dish must function with minimal degradation. Radiation can alter materials and electronics within the dish, and micrometeoroid impacts can damage surfaces. Redundant communication systems might be necessary, adding mass and power needs. Shielding also must consider the internal radiation produced by the craft itself. A nuclear reactor produces radiation. Even with distance and shielding, some radiation can reach the habitat. The reactor's shielding must be designed so that crew dose remains within acceptable limits over the mission duration. This may require heavy shielding around the reactor and careful placement. Again, mass adds propulsion cost. If the reactor's shielding is heavy, it might be placed far from the habitat, but then power must be transmitted over long distances, requiring cables and control systems. If the reactor is closer, shielding must be thicker. The craft must also manage activated materials. Neutron exposure can make some materials radioactive. This can complicate maintenance if components near the reactor become activated. Over a long mission, activated components might need to be handled, stored, or replaced, adding to the waste management and crew exposure concerns. Another shielding issue is the cumulative effect of small impacts at high speed. Even within the solar system, micrometeoroids can puncture thin walls. Spacecraft often use Whipple shields, which are multi-layer shields that break up an incoming particle so that its energy is spread across a wider area on the main wall. For an interstellar craft moving at high speed, the relative energy of impacts increases dramatically. Even tiny grains can carry enough kinetic energy to cause significant damage. This requires thicker forward shielding or sacrificial layers. Those layers add mass. They also must endure a large number of impacts over a long journey. The shield might gradually erode, requiring a very thick initial shield or a method to replenish or reconfigure it. Replenishment in interstellar space is difficult because there is no source of material. The craft would need to carry spare shielding mass, which again adds mass. This creates a tension. Going faster reduces travel time and thus reduces cumulative radiation dose, but going faster increases impact energy and thus increases the shielding needed against dust. The two hazards move in opposite directions with speed. A design that pushes speed may reduce cosmic ray exposure time, but increases dust impact hazard. A design that moves slower reduces dust impact energy, but increases time and radiation dose. This trade-off is fundamental. Shielding design also affects habitability. Thick shielding walls reduce interior volume for a given mass and can make the habitat feel confined. Over decades, confinement can affect mental health. Increasing volume can help, but volume adds structural mass. Designers may prefer to create a central safe area with thicker shielding for sleeping, and rest and larger work areas with thinner shielding. Yet in long missions, the crew's time distribution matters. If much time is spent in less protected areas, cumulative dose increases. Optimizing the layout becomes a complex problem. In this region, shielding becomes a system that spans materials, science, structural engineering, logistics, life support, and human factors. It cannot be solved by simply adding a thicker wall because mass and secondary radiation effects impose diminishing returns. It cannot be solved by simply relying on a storm shelter because cosmic rays are continuous. It cannot be solved by simply inventing a magnetic shield because generating and maintaining the required fields and structures remains unproven at scale. The realistic approach uses mass already needed, arranged cleverly with redundancy and maintainability. But this approach still carries a heavy mass and complexity burden. This burden is one of the main reasons human travel beyond the solar system remains beyond present capabilities. The craft must be both light enough to accelerate and heavy enough to protect, and those requirements fight each other at every level of design. The next region moves inward from shielding into the physical hazard of micrometeoroids and interstellar dust because impacts become a direct threat to structure systems and crew safety, and their severity changes sharply with speed. Space is sparse, but it is not empty. Within the solar system, there are micrometeoroid small grains left from comets, asteroid collisions, and the general dust population that orbits the Sun. Spacecraft routinely experience tiny impacts, and engineers design surfaces and pressure vessels to tolerate a certain rate of punctures and erosion. Beyond the solar system, the craft enters the local interstellar medium, which also contains dust grains and gas. The density is low, but the distances are vast. Even rare encounters accumulate across light years. The key issue is that impact energy depends strongly on relative speed. A grain of dust moving relative to the craft at tens of kilometers per second can cause a tiny pit. The same grain at thousands of kilometers per second carries far more kinetic energy and can behave like a high-energy projectile. If an interstellar craft aims for a significant fraction of the speed of light, then even microscopic particles become hazards with energies that are difficult to manage. This makes dust not only a material wear issue, but potentially a catastrophic risk. The physical mechanism is simple. Kinetic energy increases with the square of speed. If speed increases by a factor of 10, energy increases by a factor of 100 for the same mass. If speed increases by a factor of 100, energy increases by a factor of 10,000. Interstellar travel concepts that seek to reduce trip times often propose speeds that are far higher than those of current probes. At such speeds, a dust grain can vaporize on an impact, producing a plume of plasma and fragments that can erode and damage forward surfaces. Repeated impacts can gradually erode shielding damage sensors and weaken structures. A single larger grain, though still small by everyday standards, could deliver enough energy to penetrate protective layers and threaten pressurized compartments. The craft must therefore assume a forward hazard environment. It needs a forward shield that can absorb impacts and protect the habitat behind it. One approach is to use a sacrificial bumper shield where an outer layer is placed some distance ahead of the main pressure wall. When a particle strikes the bumper, it breaks apart and spreads, and the debris cloud then hits the main wall over a wider area, reducing the chance of penetration. This is the principle behind Whipple shielding used on spacecraft and stations. For interstellar speeds, the concept still applies, but the required thickness and spacing may need to be much larger. The shield might need multiple layers with spacing and materials chosen to handle vaporization and plasma effects. Designing such a shield for decades of exposure is difficult because the shield must withstand cumulative erosion without becoming too heavy. A thicker shield adds mass, which makes propulsion harder. A lighter shield increases risk. The shield must also maintain its shape and alignment with the craft's direction of travel. If the craft's orientation drifts, sensitive parts could be exposed. Therefore, attitude control and navigation must keep the craft pointed accurately for years. Pointing accuracy also matters because the forward shield may be designed to protect only within a certain cone. A small misalignment can expose radiators, antennas, or other structures to impacts. For a craft using a sail, the sail itself becomes an enormous target. A sail is thin and must be lightweight. It is therefore vulnerable to puncture and tearing. In the inner solar system, micrometeoroid punctures can be tolerated if they are small and if the sail has redundancy. Over interstellar distances at high speed, damage could accumulate to the point of failure. This is one reason why beamed sail concepts often focus on small probes rather than crewed craft. The larger the sail, the more area is exposed and the higher the probability of significant damage. For a crewed craft, a large sail would need to be extremely durable or repairable, which conflicts with its requirement to be light. If the craft uses external beams for acceleration, it might jettison the sail after acceleration, reducing exposure during cruise. Yet jettisoning removes the ability to use the sail for braking. This again ties dust hazard to the acceleration and deceleration problem. Interstellar dust hazard also affects the design of windows sensors and forward-facing instruments. Crewed habitats usually avoid large windows because pressure vessel windows are heavy and are potential weak points. In interstellar travel, windows become even less practical because a forward-facing window would be a vulnerability. Visual observation can instead be done through cameras behind protective shutters. Sensors can be mounted behind transparent shielding or can use periscopic paths. Yet even shielding can be degraded by impacts. Optical surfaces can be pitted, reducing clarity. Over decades, maintaining optical quality is hard. For navigation, star trackers and other sensors must continue working. They can be placed behind protected apertures or can use redundant units that are rotated into place as others degrade. Again, redundancy adds mass and complexity. Interstellar gas is another factor. Gas density is low, but at high speed, the craft effectively rams into a flow of atoms. These atoms can embed in surfaces, sputter material away, and contribute to erosion. They can also contribute to a faint drag. For very high speeds, drag might not be negligible over light years. Drag means the craft loses speed unless it continues to apply thrust. Continuing thrust requires energy and propellant or external power. Even if drag is small, the energy deposited by gas impacts can create heating of forward surfaces. This heating adds to the thermal control problem and can affect material longevity. The forward shield must therefore handle both particular impacts and atomic sputtering. Material selection becomes important. Some materials resist sputtering better. Some withstand high temperature better. But materials that are strong and heat resistant can be dense, adding mass. Another hazard is that impacts can generate secondary radiation. High-speed impacts can produce ionizing radiation in the impact plume. In extreme cases, the plasma created can emit X-rays. For realistic interstellar speeds envisioned in near-term concepts, this is a complex area and depends on particle size and speed. The general point remains that high-speed impacts convert kinetic energy into heat plasma and fragmentation, all of which must be managed. The craft must assume that its forward region is an environment of continual bombardment. Maintenance and repair in that region are difficult because it may be outside the safe habitat. External repair requires spacewalks or robotic systems. Spacewalks are risky even in Earth orbit. In deep space, a spacewalk has additional risks from radiation and from the inability to return quickly to safety if something goes wrong. Robotic repair systems could help, but they add mass and require complex control and spares. A long mission might rely heavily on robotics for external inspection and repair. This requires reliable robots, spare parts, and the ability to diagnose failures. The dust hazard also interacts with the earlier time and communication limits. If a forward shield is damaged, the crew must detect it, assess the risk, and repair or compensate without rapid support from Earth. The craft must have sensors that can monitor shield integrity. It might use acoustic sensors to detect impacts, thermal sensors to detect hotspots, and cameras to inspect surfaces. These systems themselves must survive the environment. The craft must also decide how to respond to increasing erosion. If the shield's performance declines over decades, the crew must plan to allocate remaining shield margin to the later part of the voyage, perhaps by reducing speed if possible, altering orientation, or using additional sacrificial layers. Yet reducing speed may not be possible without propulsion, and carrying spare shielding mass is expensive. This makes the initial design critical, but predicting the exact dust environment along the path is difficult. The interstellar medium varies in density and dust content. The Sun moves through different regions of the local interstellar cloud environment. A voyage to a nearby star would pass through a region with properties that can be estimated but not mapped in fine detail. This uncertainty forces conservative design. Conservative design adds mass. In this region, the micrometeoroid and dust hazard reveals another trade-off that undermines the idea of straightforward high-speed travel. Faster travel reduces trip time and reduces exposure to some risks that accumulate with time, such as cosmic ray dose. But faster travel increases the energy of impacts and therefore increases the required shielding and structural robustness. Slower travel reduces impact and energy, but increases time, increasing radiation dose and increasing the burden on life support and reliability. There is no speed that makes both hazards small. The mission must choose a compromise, and the compromise still lies far beyond current crewed mission experience. The hazard also reinforces that small robotic probes are far easier than crewed ships. A probe can be compact, heavily shielded relative to its size and can accept partial failure. A crewed craft must protect a large pressurized volume and must keep it intact without leaks and without disabling damage. Even a small puncture can be serious if it occurs in a pressure vessel. Leak repair is possible, but repeated leaks and structural weakening over decades is a major risk. The dust environment, therefore, is not a minor detail. It is a defining constraint that shapes the feasible cruise speed, the required mass, and the need for autonomous monitoring and repair. Strengthens the conclusion that human travel beyond the solar system remains impractical because the environment is not merely far away. It's actively abrasive and hazardous in ways that scale with the very speeds needed to make the trip short enough for human life. The next region moves inward from physical impacts into navigation and course control, because over interstellar distances, small errors become enormous and correcting them requires fuel time and precise measurement. Navigation in space begins with knowing where the craft is and how fast it is moving. In the inner solar system, this is achieved by tracking radio signals from Earth by using known positions of planets and spacecraft, and by modelling gravitational forces. A craft can receive frequent updates and can execute corrections with relatively small burns. Even if the craft is far away, a correction of a few meters per second can adjust the trajectory enough to reach a planet. Over interstellar distances, the geometry changes. A tiny pointing error at departure and error that might be negligible over a trip to Mars becomes a huge lateral displacement after years of travel. The craft's path is essentially a long straight line with slight curvature from gravitational influences and from small forces like radiation pressure or outgassing. If the craft must arrive at a target that is effectively a moving point at the end of that line, then its trajectory must be set with extraordinary precision. The target star itself is moving relative to the Sun and has its own velocity through the galaxy. It also has planets that orbit it. If the goal is merely to pass near the star, the target region can be larger. If the goal is to enter a particular orbit or to approach a specific planet, the target region shrinks dramatically. In that case, the craft must not only aim accurately, but also time its arrival so that the destination planet is in the right place. Timing errors translate into spatial errors because planets move along their orbits. Over decades, even small uncertainties in the destination system's planetary ephemerides can grow. Astronomers can predict planetary motions very precisely within our own solar system, but for exoplanet systems the data is less complete. Even if an exoplanet is known, its orbital parameters have uncertainties. An interstellar mission would require years of continued observation from Earth to refine those parameters. Yet the craft may spend decades en route and the system may have additional planets not detected. The navigation challenge therefore includes incomplete knowledge. A crewed craft must be prepared to adjust its plan on arrival based on what it finds, which requires onboard sensing and the ability to change course and speed. This loops back to propulsion and to fuel margin. Navigation also depends on tracking the craft from Earth. Radio tracking over interstellar distances faces limitations. Signals weaken with distance because they spread out and there are limits to transmitter power and antenna size. Large antennas can be built, but maintaining a strong link over light years is demanding. The craft can carry a powerful transmitter and a large dish, but these add mass. A laser communication system can provide higher data rates for a given power by narrowing the beam, but narrow beams require extremely precise pointing. Over light-year distances, a pointing error of a tiny fraction of a degree can miss Earth by millions of kilometers. This precision can be achieved with star trackers and fine control, but maintaining it over years, while the craft vibrates, expands and contracts with temperature changes and experiences impacts, is difficult. Communication and navigation are intertwined. Tracking requires communication. Communication requires pointing and stable attitude. Stable attitude requires control systems and sometimes propellant. Over a long mission, propellant used for attitude control becomes a budget item. Reaction wheels can control attitude without propellant, but they can saturate and require momentum dumping, often using thrusters. Reaction wheels can also fail due to wear. A decades-long mission must either carry multiple redundant wheels and spares or use alternative control methods. Control moment gyros, thrusters and magnetic torquers all have limitations, and magnetic torquers are not useful far from planetary magnetic fields. Therefore, a deep spacecraft must rely on internal momentum exchange and small thruster firings. Thrusters consume propellant. Propellant is limited. A crewed craft already needs propellant for course corrections and perhaps for braking. Using propellant for attitude control competes with these needs. A design that minimizes attitude control propellant might accept less frequent reorientation, which can constrain thermal management and communication pointing. Again, systems interact. Onboard navigation can use stars and pulsars as references. Star trackers can measure the craft's attitude by comparing observed star patterns with catalogues. This gives orientation. Position is harder. One method is to use optical navigation by measuring the angles between known stars and nearby objects. Another method uses pulsar timing. Pulsars are rotating neutron stars that emit regular pulses of radiation, often in X-rays. By measuring the arrival times of pulses from several pulsars, a craft can estimate its position, similar in concept to a global navigation system, but on a galactic scale. This method is actively studied and could provide autonomous navigation without Earth tracking. However, it requires sensitive detectors, stable clocks, and complex algorithms. It also has limitations in accuracy depending on detector capability and pulsar timing stability. For an interstellar mission, such navigation could be valuable, but it adds complexity and equipment that must operate for decades. Clocks drift over time and must be calibrated. Detectors degrade under radiation. Calibration without Earth support becomes difficult. Even if onboard navigation can estimate position, course corrections require propulsion. Small errors can be corrected early with small burns. The longer an error persists, the more correction is needed later. This suggests a mission strategy where the craft performs frequent small corrections early using precise measurement. Yet frequent corrections consume propellant and require engine firings which can stress systems and introduce vibration. If the craft uses a low-thrust propulsion system for cruise, it might adjust its trajectory continuously rather than in discrete burns. This can be efficient but requires the propulsion system to operate reliably and to be controllable with high precision. If the craft coasts for most of the journey and relies on a few major burns, then the accuracy of those burns becomes critical, and any mismatch can lead to large errors. In addition, if the craft must decelerate near the destination, the timing and direction of deceleration must be precise. Deceleration changes the craft's trajectory and can be used to steer as well as to slow down. But steering while decelerating requires vectoring thrust or orienting the craft, which interacts with shielding and thermal constraints. For example, the craft may prefer to keep its forward dust shield facing the direction of travel. If it needs to steer, it might need to tilt the craft, exposing parts of the structure to dust impacts. Alternatively, it might use side thrusters, but that consumes propellant and requires additional shielding and thermal management. Navigation at interstellar distances also faces the problem of gravitational influences. The galaxy's gravitational field and the pull of nearby stars can slightly alter the trajectory over decades. These influences are small but not zero. Modelling them requires knowledge of the local mass distribution. Most of the mass in the galaxy is not visible, and the distribution of interstellar gas and dark matter is inferred rather than directly mapped at high resolution. For practical navigation over a few light years, gravitational perturbations from nearby stars and the galaxy can be modelled with sufficient accuracy, but uncertainties remain. Small errors in gravitational modelling translate into trajectory errors over long time. This reinforces the need for onboard measurement and correction. It also means that the craft cannot simply point at the destination and coast without monitoring. It must continually assess its path. The need for continual assessment again pushes toward autonomy and toward robust systems that can operate without human micromanagement. A crewed craft might have humans performing navigation oversight, but humans rely on instruments. The instruments must be reliable. The crew must also handle other duties such as maintenance and life support. Navigation becomes one more persistent task. In this region, the overall picture is that interstellar travel is not like crossing an empty sea where direction can be adjusted casually. It is more like aiming a needle across a continent, where small departures at the start become vast misses at the end, and where the ability to correct depends on carrying limited resources. The distance makes precision essential, and precision requires stable systems, continuous measurement, and careful control. Each of these demands power, mass, and reliability. These demands do not by themselves make the journey impossible, but they add to the already heavy burden of propulsion, shielding, and life support. They also show that a crewed interstellar craft must be a long-duration precision machine, not only a powerful engine. It must keep itself pointed, tracked, and corrected over years, while its own structure changes with heat, while its surfaces are eroded by dust, and while its electronics face radiation. Navigation becomes another layer where long time transforms small imperfections into mission-ending failures. The next region moves inward from navigation into communication delay and operational autonomy, because beyond the solar system, the craft cannot be run as an extension of Earth. Communication across space is limited by signal strength and by the speed of light. The signal strength problem can be improved by larger antennas, higher power transmitters, and more sensitive receivers. The speed of light cannot be improved. This means that beyond a certain distance, communication becomes inherently asynchronous. In the outer solar system, one-way light time delays already prevent real-time control. Operators on Earth send sequences and wait. The craft executes its plan and returns data later. This mode works for robotic missions because the craft's objectives can be planned in advance, and because the craft can wait in safe configurations if something unexpected happens. For a crewed interstellar mission, the same pattern becomes more extreme. If the craft is a light year away, a message takes 1 year to arrive. If it is 4 light years away, it takes 4 years. The crew cannot treat Earth as mission control in any operational sense. Even routine updates arrive too late to guide decisions. Emergency support is effectively absent. The craft must function as a self-governed operational unit with onboard capabilities for planning, diagnosis, repair, and decision-making. Autonomy begins with systems. In modern spacecraft, onboard fault detection and recovery already exists. A spacecraft can detect a power anomaly switch to backup systems and enter a safe mode. For long missions, safe mode must be more than a temporary pause. It must keep the craft stable for long periods while problems are diagnosed and repaired. For a crewed craft, safe mode must still maintain life support and thermal control. This demands robust automation. Yet automation must be trustworthy. A faulty autonomous response can be dangerous. Therefore, autonomy systems must be extensively tested and their behavior must remain predictable even after years of software updates, component aging, and unexpected interactions. Software itself becomes a reliability concern. Complex software can contain rare bugs that appear only under certain conditions. Over decades, conditions will vary. Radiation can also cause memory bit flips and other errors requiring error correction and fault-tolerant computing. A crewed craft must include computers that are both powerful and robust with redundancy, and the ability to isolate faults. The crew must also be able to understand and override automation when necessary. This requires training and clear system design. If the mission lasts decades, crew members may be born and raised on the craft if the mission is multi-generational, or they may age significantly during the mission. Maintaining operational competence across time becomes a social and educational problem as well as a technical one. Communication delay also changes the nature of knowledge exchange. In near-Earth missions, the crew can consult specialists on the ground for medical advice, engineering, guidance, and scientific interpretation. In a distant mission, consultations arrive too late to address immediate issues. The crew must carry the expertise. This implies a larger crew or a more broadly trained crew. A larger crew increases life support needs and habitat volume. A more broadly trained crew implies longer training and possibly more crew time dedicated to education during the mission. The craft may carry extensive digital libraries, but using information effectively under stress requires practice. Medical autonomy is especially challenging. Even in Earth orbit, medical capability is limited and relies on ground support. In interstellar space, the crew must diagnose and treat illnesses without real-time consultation. They must handle trauma infections, chronic conditions, and potential radiation-related effects. They must also handle dental issues, surgical emergencies, and psychological crises. Carrying a full hospital is not feasible. Therefore, the mission must either accept significant medical risk or develop compact medical systems and protocols that can handle many cases. Even with advanced medical equipment, there is the issue of supplies. Medicines have the shelf lives. Some degrade over time, especially under radiation and temperature variation. Sterile supplies must remain sterile. A decades-long mission must include either long-lived medical stores or the capability to synthesize certain medicines on board. On-board synthesis would require chemical processing equipment, raw materials, and quality control. This again adds complexity and power demands. Operational autonomy also includes governance. A crewed craft is a small society. It must allocate resources, schedule maintenance, resolve conflicts, and make mission-critical decisions. In near-term spaceflight, crews rely on Earth institutions for policy and authority. In interstellar travel, Earth authority cannot act quickly, and Earth's cultural and political context may change over the mission. The crew must have its own decision structures. This is not a philosophical add-on, it is an operational necessity. Without clear decision processes, emergencies can spiral. Designing governance for a long isolated mission is difficult because it must balance flexibility with stability. It must handle leadership succession conflicts and the possibility of divided opinions on risk. The need for autonomy therefore extends beyond engineering into human organization, which must be robust enough to function without outside arbitration. Communication delay also affects resupply and repair. In the solar system, a craft can be sent supplies at least in principle, though the practicality depends on distance. Beyond the solar system, resupply is not practical. Even sending a small package would take years and would require precise targeting. The craft must carry all necessary materials or be able to produce them. This suggests onboard manufacturing such as machining, additive manufacturing, and electronics repair. Manufacturing in space is possible in limited forms, but producing complex components like microchips, high-precision bearings, and advanced composites requires industrial infrastructure and cleanroom conditions. A craft that aims to be fully self-sustaining would need a miniature industrial base. This would add mass and complexity beyond what current spacecraft carry. Therefore, practical autonomy may rely on carrying a large inventory of spares for critical systems. Spares add mass. The probability of needing a particular spare is hard to predict over decades. Designers might carry multiple spares for high-risk components and fewer for low-risk ones, but rare failures become likely over long time. This creates a tension: either carry many spares, making the craft heavy, or accept the risk that an unanticipated failure cannot be repaired. Communication delay also changes the nature of mission updates. Scientific goals may evolve as new discoveries are made on Earth. A mission to a particular star system might launch with one set of expectations, but by the time it arrives, Earth's knowledge may have changed. New exoplanet discoveries might revise the perceived value of the target, yet the craft cannot easily change destinations without large energy and time costs. The crew may receive new priorities years after leaving. The crew must decide whether to follow them. This again requires autonomy and a stable mission framework. The craft becomes a long-term commitment that cannot be adjusted quickly. This reduces flexibility compared with many exploration missions. The operations of the craft must also handle the reality of limited communication bandwidth. Over interstellar distances, even with large antennas, data rates may be low. The craft might need to compress data, prioritize critical information, and accept that many details cannot be transmitted. The crew may need to make decisions based on local observations that Earth cannot fully review. This increases the importance of onboard scientific competence and instrumentation. The crew may also need to maintain the communication system itself, which includes high-power amplifiers, pointing mechanisms, and potentially laser optics. Aligning a narrow beam to Earth requires precise knowledge of Earth's position in the sky, which changes as the Sun and Earth move through the galaxy. The craft must account for the proper motion of the Sun and the destination star system. It must also predict where Earth will be years later when a message arrives. This is possible with celestial mechanics and galactic motion models, but it adds complexity and requires accurate clocks. Clock stability over decades is itself a challenge. Atomic clocks can drift. Radiation can affect electronics. The craft must keep time precisely to maintain navigation and communication protocols. In this region, autonomy becomes a defining characteristic of any mission beyond the solar system. Autonomy is not a luxury. It is forced by light travel time and by the absence of resupply. Achieving autonomy requires robust engineering, extensive redundancy, maintainability, and a crew capable of handling technical and social challenges without external help. Each of these requirements adds mass power use and complexity. Each increases the burden on propulsion and on shielding. The mission becomes a closed system where every failure must be met internally. The longer the mission, the more likely failures become. This is why even if a propulsion method could accelerate a craft toward another star, the operational realities of autonomy and delay remain a major barrier to crewed interstellar travel. The craft must carry not just a crew and an engine, but a resilient, self-supporting operational world. The next region moves inward from autonomy into closed life support and long-term reliability because sustaining human life for decades without resupply is a biological and engineering challenge that is still only partially solved even for shorter durations. Life support begins with air. Humans need oxygen and produce carbon dioxide. In a spacecraft, oxygen must be supplied and carbon dioxide must be removed. Oxygen can be stored as compressed gas, as chemical compounds, or generated by splitting water. For long missions, storage alone becomes too heavy and bulky. Generation and recycling become essential. Carbon dioxide can be removed with chemical scrubbers or regenerative systems that capture it and release it later for processing. Some systems can convert carbon dioxide and hydrogen into water, and methane recycling part of the oxygen. Yet no life support system is perfectly closed. There are losses through leaks, through incomplete recovery, through chemical side reactions, and through maintenance and filter replacement. Over years, small losses accumulate into large deficits unless the system is extremely efficient. Maintaining a closed atmosphere also requires controlling trace contaminants. Humans and materials release volatile compounds. Equipment can off-gas. Cleaning products and plastics can release chemicals. Over time, these trace compounds can build up unless removed by filters and catalytic systems. Filters saturate and must be replaced or regenerated. Catalysts can degrade. A decades-long mission must either carry large supplies of replacement media or have the capability to regenerate them. Regeneration can require high-temperature processing vacuum systems and chemical reagents. Each adds power, needs, and complexity. Water is another core requirement. Water is needed for drinking hygiene, food preparation, and oxygen generation if electrolysis is used. Current space systems can recycle water from urine and humidity condensation with high efficiency, but not 100%. Over long durations, even small inefficiencies mean large losses. Water can also be lost through leaks, through contamination, and through storage failures. A long mission must manage water, carefully maintaining redundancy in storage and recovery. It must also manage microbial growth. Water systems can develop biofilms that clog filters and cause contamination. Maintaining water purity requires sterilization methods, such as filtration, chemical treatment, ultraviolet exposure, or heat. Each method has operational and material impacts. Chemicals must be replenished. Ultraviolet systems require lamps or solid-state emitters that can degrade. Heat sterilization requires energy. Managing water is therefore a constant task, not a one-time design. Food is the most challenging consumable. For a mission lasting months, food can be carried. For years, food mass becomes large. For decades, carrying all food becomes impractical, unless the crew is very small and the mission accepts extreme constraints. Food also has shelf life. Some foods can be stored for years, but quality and nutritional value can degrade. Vitamins can break down. Fats can go rancid. Packaging can fail. Therefore, a decades-long mission likely requires some form of food production. Food production implies agriculture in a closed environment. Plants can produce food and also contribute oxygen, but they require light, water, nutrients, and space. Light can be provided by electric lamps which consume power and produce heat. Plants also transpire water which must be recovered. They can harbour microbes and pests. They require careful nutrient cycling. Nutrients include nitrogen, phosphorus, potassium, and trace elements. These must be recycled from waste streams. Human waste can be processed into fertilizers, but doing so safely requires controlling pathogens and odors. Waste processing systems must be robust, and any failure can threaten health. Growing enough food to sustain a crew requires significant area or volume depending on the cultivation method. Hydroponics and aeroponics can be efficient, but they rely on pumps, sensors, and controlled chemistry. Soil-based systems may be more forgiving in some ways but require mass and can be harder to sterilize. All methods add complexity. For a long mission, food production might cover only part of the diet, with stored staples providing the rest. Even partial production reduces dependence on stored food and adds psychological benefits through fresh produce. Yet it adds failure modes. A crop failure in space is not simply a loss of comfort. It could become a nutritional crisis. Therefore, food production systems must be redundant and diverse. Diversity in crops and methods reduces risk but increases complexity and space. Space increases structural mass and shielding needs. Reliability is the overarching issue. Life support systems include many pumps, valves, sensors, filters, membranes, and software controllers. Each component has a failure rate. Over decades, failures become likely. Redundancy can help, but redundancy also requires additional components which also can fail. Maintenance becomes continuous. Crew time becomes heavily allocated to upkeep. In Earth-based closed environments such as submarines and Antarctic stations, resupply and evacuation are still possible, and the environment is not subject to vacuum and radiation. Space adds these hazards and removes resupply. A crewed interstellar craft must therefore achieve a level of reliability and maintainability beyond current closed habitat experience. Materials must resist outgassing, corrosion, and microbial growth. Seals must remain tight. Pressure vessels must withstand fatigue and impacts. A small leak in a pressurized habitat can be managed if detected early, but repeated leaks or a major breach can be catastrophic. Leak detection systems must be sensitive. Repair methods must be reliable. Patching in space can be done, but doing it repeatedly over decades becomes a substantial risk. Life support closure also requires managing the atmosphere's composition over time. Oxygen levels, carbon dioxide levels, humidity and pressure must remain within safe ranges. Small drifts can affect health. Sensors must remain calibrated. Calibration is hard without external reference. Sensors can drift. Chemical sensors can degrade. The craft may carry calibration gases or reference standards, but these can also change over time. The system must include self-checking and cross-checking. Multiple sensor types can verify each other. This increases redundancy but adds complexity. In addition, the craft must manage fire risk. In a closed oxygen-rich environment, fire can spread quickly and smoke and toxic gases can be deadly. Fire suppression in space requires careful design. Water-based suppression can damage electronics. Foam and chemical suppressants can contaminate air. Inert gas suppression can reduce oxygen and threaten breathing. Fire detection systems must be reliable. Materials must be flame-resistant. The crew must be trained. Over decades, the probability of an electrical fault or human error that leads to fire increases. Therefore, fire safety is a central long-term design concern. Microbial control is another persistent issue. Humans carry microbes. In a closed environment, microbes can colonize surfaces, air ducts, and water systems. Some can cause illness, some can degrade materials. Keeping microbial populations controlled requires cleaning, filtration, and perhaps ultraviolet sterilization. Cleaning supplies must be stored or produced. Filters must be replaced. Waste must be handled hygienically. The craft becomes an ecosystem where biology and engineering are interwoven. Stability requires active management. Psychological factors also tie into life support. A long mission requires stable routines, adequate sleep and exercise, and mental health support. Exercise is necessary to maintain muscle and bone health, especially if artificial gravity is not continuous. Exercise equipment consumes space and produces vibration and heat. Mental health support may include private space communication with Earth and meaningful work. Communication delay limits real-time conversation. The crew may experience isolation. The habitat design must support privacy and community, yet increasing space increases mass. There is a constant tension between the needs of human well-being and the constraints of mass and shielding. Reliability also includes spare parts and tools. Every pump valve and filter that might fail must have a replacement or a repair pathway. For decades, the inventory becomes large. Storing spare parts requires space and adds mass. Manufacturing spares on board is possible for some items, but not all. Manufacturing requires raw materials and machines. It also requires quality assurance because a poorly made part can fail. Quality assurance requires measurement tools and standards. Each layer adds more equipment. The craft approaches the complexity of a small factory. This is far beyond current spacecraft. In this region, the combined picture of closed life support and reliability shows why human travel beyond the solar system is more than a propulsion challenge. Even if a craft could be sent toward a star, keeping humans alive and healthy for decades without resupply requires a closed ecological and mechanical system with extraordinary stability. Current technology can support crews for months and with resupply for years. Fully closed long-duration systems remain difficult with ongoing research and partial demonstrations. Extending this to interstellar durations adds the compounded risk of component failure, microbial shifts, nutritional degradation, and psychological strain. The need to solve all of these within a mass budget that also includes shielding and propulsion makes the mission extremely challenging. It becomes an exercise in maintaining a small world against the steady pressure of time, without outside help while moving through a hazardous environment. The next region moves inward to the smallest scale the human body and mind over long duration, because even if propulsion, shielding, autonomy and life support are engineered, the crew remains a biological system with limits that are difficult to extend across decades of isolation and cumulative exposure. Human physiology is adapted to Earth's gravity day-night cycles and a rich environment of medical support. In space, even within Earth orbit, astronauts experience changes in fluid distribution, muscle, and bone loss vision. Changes, immune alterations, and changes in sleep and mood. Many of these effects are linked to weightlessness. If an interstellar craft uses sustained acceleration to provide artificial gravity, some of these effects may be reduced. Yet sustained acceleration at a comfortable level may not be achievable for the entire mission due to power constraints. If the craft spends long periods coasting in microgravity, then countermeasures become necessary. Countermeasures include exercise, which can reduce muscle and bone loss but requires discipline, equipment, and time. Over decades, maintaining consistent exercise routines is difficult, especially under stress and with limited variety. Equipment also wears out. Treadmills, resistive devices, and harnesses require maintenance. A failure in exercise capability can lead to accelerated health decline. Even with exercise, microgravity affects the body in ways not fully prevented by current countermeasures. Vision changes, for example, have been observed in astronauts and involve fluid pressure and structural changes in the eye. The long-term progression of such changes over decades is uncertain. Uncertainty itself is a risk because the mission cannot easily adapt if a chronic condition emerges that is not well understood. Radiation adds another slow burden. The cumulative exposure to galactic cosmic rays increases cancer risk and may affect the cardiovascular system and the nervous system. These risks are probabilistic. Not every individual will develop disease, but the likelihood increases with dose and time. In a long mission, the crew is exposed for years. Even if shielding reduces dose, it may not reduce it enough to make risks comparable to life on Earth. The crew also may be exposed to occasional higher dose events. Over decades, the probability that at least one crew member develops a serious condition rises. Medical capability on board must be sufficient to diagnose and treat as much as possible. Yet medicine in a closed environment faces limits. Surgery in microgravity is challenging, sterility is harder to maintain. Medical imaging and laboratory analysis require equipment and supplies. Some treatments require pharmaceuticals that may degrade over time. Advanced treatments like radiation therapy are impossible in a spacecraft. The crew must therefore accept a level of medical risk that is higher than on Earth. This risk is not only personal but operational, because a serious illness can reduce the crew's ability to maintain the ship. In a small crew, losing one specialist can create cascading vulnerabilities. Therefore, mission design often suggests larger crews for redundancy and skills. Larger crews require more life support and more space. Again, mass and complexity rise. Aging is another constraint. A decades-long mission means the crew ages significantly. Aging brings increased risk of cardiovascular disease, reduced bone density, reduced immune response, and slower healing. Even in ideal conditions, aging changes performance. In the confined environment of a spacecraft with altered gravity and chronic radiation exposure, aging effects may be accelerated or complicated. Designing a mission where the same crew remains healthy and competent for decades is therefore uncertain. A mission could be designed as a multi-generational voyage where children are born and raised on board. This introduces additional biological and ethical constraints. Pregnancy and development in space are not well understood. Radiation exposure during development is especially concerning. A closed habitat would need education systems, social structures, and medical support for childbirth and pediatric care. The mission becomes not a crewed expedition, but a migrating population. The complexity increases greatly. Even if this concept is set aside, a mission of a few decades with an adult crew still confronts aging and the need for long-term health maintenance. Nutrition becomes crucial. On a long mission, maintaining a balanced diet with stable micronutrient content is hard. Stored foods can lose vitamins. Food production systems may provide fresh produce, but crop variety may be limited. Nutritional deficiencies can develop slowly and impair immune function, cognition, and physical strength. Monitoring nutrition requires medical testing. Testing equipment must be reliable. Treating deficiencies may require supplements that must remain potent. Sleep and circadian rhythm management is also important. In deep space, there is no natural day-night cycle. The habitat must create an artificial light schedule. Lighting affects sleep quality, mood, and cognitive performance. Lighting systems must be adjustable and stable. Over years, changes in routine stress and work demands can disrupt sleep. Chronic sleep disruption increases accident risk and reduces immune function. A long mission must therefore treat sleep as a critical system, not a personal preference. The mind is as constrained as the body. Isolation and confinement are known stressors. Even on Earth, in polar stations and submarines, crews experience mood changes, interpersonal conflict, and cognitive strain. Those environments still allow eventual return and still operate under Earth's social context. In interstellar travel, the absence of return in a practical time frame changes the psychological landscape. Even if the mission includes a planned return, the return time may be so long that it becomes abstract. Communication with Earth is delayed by years. This makes relationships different. Messages become more like letters than conversations. Emotional support from Earth is limited by delay. The crew must rely on each other and on onboard routines. Conflict resolution becomes critical. Small irritations can grow over long time. The crew must have mechanisms for privacy, for recreation, for creative expression, and for managing stress. Yet providing these requires space materials and time. Space is constrained by mass. Time is constrained by maintenance demands. The crew may be burdened by constant repair work, leaving less time for rest. Burnout becomes a risk. Cognitive performance also depends on stimulation and variety. A long mission has limited environments. Without variety, attention and motivation can decline. Virtual reality and media libraries can help, but they require power and equipment and may not fully substitute for real environments. The crew must also maintain a sense of purpose and routine without constant feedback from Earth. Purpose is not a philosophical requirement here. It is an operational factor. People function better with stable goals and coherent schedules. A mission that lasts decades must maintain these structures. Unexpected failures and ongoing hazards can erode morale. The crew must therefore be selected and trained for resilience, adaptability, and cooperation. Selection can reduce risk but cannot eliminate it. People change over time. Stress can reveal traits not seen in training. Long missions magnify small vulnerabilities. There is also the risk of accidents and injuries. Even in a stable habitat, accidents happen. A slip, a tool injury, a burn, or an infection can occur. In a long mission, the probability of such events rises. Recovery may be harder without advanced medical care. Even minor injuries can reduce capacity. This returns to the need for redundancy in skills and for a margin in crew capacity. A crew that is just large enough for normal operations may be too small after injuries and illness. Increasing crew size increases life support and shielding needs. The human scale therefore closes the chain of constraints. Distance imposes time. Time imposes accumulated risk and autonomy. Autonomy imposes complexity and maintainability. Complexity imposes mass. Mass imposes propulsion and energy demands. Energy demands impose heat and shielding. Shielding and speed impose impact hazard. All of these press inward until the limits of the human body and mind become the final filter. The phrase never in popular titles often compresses this chain into a single dramatic claim, but the practical conclusion is quieter. With present technology and foreseeable near-term engineering, the combined demands of speed shielding, life support, closure reliability, and human health over decades make crewed travel beyond the solar system impractical. The human organism is not designed for decades in a sealed can exposed to chronic radiation sustained by machines that must not fail with no timely rescue and no real-time contact with the world of origin. The gap between what is required and what is currently demonstrated remains wide, not because of one missing discovery, but because many narrow margins must all be met at once for a very long time. This is where the journey ends at the scale of breathing blood flow, sleep and calm decision-making, because beyond the solar system those small processes must endure longer than any human space voyage has ever demanded. It is on this smallest scale that the practical barrier becomes most clear. Word count 1391. Awaiting continue wind down. The craft continues onward in the dark and the problems remain steady rather than dramatic. The distance keeps time long. The time makes every small risk accumulate. Power must flow without interruption, and heat must be moved and radiated away day after day. Water and air must be kept clean and kept within narrow limits. Shields must hold against radiation and against the quiet abrasion of dust. Navigation must remain precise with small corrections made before errors grow. Communication remains slow arriving as delayed echoes. Inside bodies must sleep, eat, exercise and heal, while minds keep routine and cooperation through long months and years. Each requirement presses on the next and none can be neglected without consequence. The solar system, with its sunlight and its closeness, recedes into a distant point not as a symbol, but as a reminder of how much support normal missions quietly rely on. Beyond that support, a human journey becomes an attempt to keep a small engineered environment stable for longer than its parts are proven to last while the crew ages and while the environment remains indifferent. The result is not a statement about what can never happen in principle. It is a description of what remains out of reach when all constraints are considered together. The most direct path to other stars for now remains through instruments and signals through telescopes that read faint light and through probes that can endure long time without the demands of a living body. In the quiet scale of space, this is enough to learn, measure, and understand without placing human life inside the narrow margins that an interstellar voyage requires.